accelerated motion, but only one-dimensional so far. Now we're going to two-dimensional. So we're going to talk about examples of projectiles. I've gone over that a lot of times already. We'll talk about the path, and then we'll talk about this last part, which is going to take us a couple days actually to do. We're going to spend probably 3 to 4 full class periods on this topic. Now, each day we're going to have a different focus. Today the focus is going to be the introduction of what this is and the beginning problem of what's called the horizontally fired problem. We'll spend a day or two on that. Then we're going to go to the problem where it's fired at an angle, and we see that the projectile makes a parabola that has some symmetry. And then we'll move on to problems where, what if it's fired at an angle and it's not symmetric? What if it lands at a higher height? Or what if it starts higher and lands lower? So very similar to the type of problems we've already done for vertical motion only, where it's launched and lands below, or launched and lands above, or launched and lands right back at the ground. We're going to take the same kind of approach, but in this lesson it's going to be launched at an angle instead of vertically itself. The horizontally fired we'll talk about first, because that's a bit of a different one there. So let's first talk about the word projectile. So any moving object that can be modeled as a point, physically, as a point, is considered a projectile. So in this case, we're talking about projectile motion. We're talking about two-dimensional motion. So a runner in this case is running, and as she does a long jump in this example, landing at the very end, we consider the fact that the person here has velocity in the x and velocity in the y. The only way you can launch yourself in the horizontal direction and the vertical at the same time is by pushing off at an angle. And think about this logically. If you've ever, now I'm not saying everybody here is a track star, but if you've ever tried to hurdle over something, not saying you have to be a hurdler, but if you've actually tried to jump over another object, you're doing this every time. You can't physically just jump and not move horizontally and vertically at the same time. This way is all vertical. This is all horizontal. But if you try to jump over an object, literally, you have to move in both directions. So you have to have velocity in the x and in the y. So really, the runner and the jumper in this case pushes off at an angle. And that's where we went into vectors. When we said something like a vector was at an angle, we broke it into the horizontal component, like in this case vx, and the vertical component, vy. God bless you. Let's talk about two types of paths for projectiles. These are some old figures. Nice soccer player here. The blue path is the path where we assume no air resistance. We assume no air resistance. And there's perfect symmetry if we assume no air resistance. We've assumed no air resistance for all problems unless stated otherwise. And that's what was on the last test. That's what's been in all of our notes so far. So we are going to continue with that same rule. There's always no air resistance unless specified elsewise. So here, the path in the black dashed line would be if there were air resistance. That's the only difference there. So the normal path without air resistance will show symmetry. The path with air resistance will not be symmetric. There will be asymmetries or an asymmetric path. Okay, an asymmetric path. So let's go right into this first example. So this is the first one that I like to look at. And this can be easily demonstrated. For today, I'm going to demonstrate it with simply an object or two. And then tomorrow, in the next class, we're going to use a little apparatus that launches objects for us. And it's actually pretty cool the way it works. So, let's take a look. This is the interesting part. So we're going to do a quick demo. It's very simple to actually do this. I'm not exhausted this time. We're going to roll them instead. So the idea is this. We're going to roll one of these objects off the table, and the other one we're going to drop at the exact same moment that the first object leaves the table. And this concept here is that if I fire an object horizontally, I'm only giving it x velocity. Think about firing an arrow from like a bow and arrow. You're literally firing it, assuming you're not arching your back or angling, right? Assuming you're firing it parallel to the ground, you are giving it all the velocity in the x direction. So what's the velocity in the y direction to start? It's just 0. It's just 0. So if I launch an arrow in the x direction only, but if I drop an arrow, they should land at the same time. Because remember, what affects the y direction is gravity and the initial velocity. Well, we just said that if we fire a bow and arrow, or an arrow from a bow, it only has horizontal velocity. It's as if we're dropping the arrow at the same time. So you want to help this one? You want to do that part? So what's going to happen is this. Thomas is going to try to roll this ball and release it like back here so it has a little bit of room. And not too fast, okay? It's going to go like at a decent speed, but not right You can drop it at the exact same moment from the exact same height, so actually move off the table a little bit right there. So what you need to do is as soon as this object clears the table, like clears this path, you have to drop it. Now, you can stay there and do it, or you can wait right here and watch it happen. And as it crosses, you can watch it. I think that's more precise. Watch it real quick. So why don't you stand over here on this side, or actually put the ball over here, but don't hit this little leg here, right? Maybe put it like here at the same height. Try not to get his to actually hit it. As soon as it crosses the path, let go. It's close. Try again. It's all right. And unfortunately, these are balls. And last year I did it with 2 tennis balls, but I don't have 2 right now. You drop your place and run. Yeah. And that's okay. No, this is good. This is good. We got comments, right? Be nice to him. Be nice to sit here. And this might be good. Sounds closer or no? Yeah. It's time to everybody sit. All right. We can do this too, okay? We can use these two so it's a little more obvious. So this is going to make a louder sound, this one's not. But for the people nearby that can view in the front, for the people in the back, feel free to stand up. If you want to see it physically happen, we should visibly see this happen. So when you move it off, we get the idea. One more time. We get the idea.
Never like figured it out 3 years after college.
Not bad. All right, so toss back. So the idea behind this is that we want to see the objects. We want to see the objects landing. Listen. Landing at the same time. Now, what you see in front of you, what is this called? Anyone know if knows art or photography well? I forget the actual name of this type of photography where you keep the lens open the whole time and it takes pictures every couple seconds and it develops that same image on the same picture. Like literally prints out like this. It's a famous type of photography that an artist invented a long time ago. You expose the lens the whole time so that you literally are taking 10 pictures and you could like see the movement of a person as they're running for a picture, and you literally see it like a flip book. You ever seen a flip book? But you see it all in one picture. Anyway, it's like open lens photography or something. What is it?
Is it like stop motion?
Stop motion?
Yeah.
Sounds close, right? Does that sound right? You can Google to see for sure. But that sounds reasonable. Stop motion.
Stop motion is like videos where you take multiple pictures and then you create one video. Yeah, that's what it is. Yeah, but that's
this is more like, yeah, so it is a little different because this is not a video, this is a picture where the lens is kept open. So what happens is this. The object in red and the object in green are both launched in a sense at the same time. The one in green is launched horizontally, the one in red is dropped. So in both cases, neither has vertical velocity. Yes, they both develop vertical velocity as they fall. The green one has horizontal velocity, and it continues to develop more vertical velocity with the horizontal as it falls. Notice what shape is this path. It's half of a parabol. Half a parabola. Parabolic shapes. Projectiles follow parabolic shapes. So we only see half of it, and that makes sense. Think about it. A bow and arrow launch falls eventually, doesn't it? It keeps falling, keeps falling, keeps falling. That's the shape we're going to see. But what you'll notice is, every single instant in time, if this is done exactly at the same moment, the objects are at the exact same height. They fall at the exact same rate. Why again? Because there's no vertical velocity to start. So we are going to look at problems now. We're going to have objects launched horizontally. So we'll have VI, but we're going to give it VIX, we're going to call that, in the X direction. And the Y velocity, we're going to say this is 0. Even if it's fired horizontally, the Y velocity, it's like you're dropping it. It's the same thing. Because these two things take the same time, they follow the exact same flight trajectory vertically. Horizontally, they're very different. The red one doesn't move horizontally. The green one does. It just moves to the right. But they're both moving up and down at the exact same, or in sync with one another.
Doesn't the one on the right have like a higher distance?
Absolutely. No, this will have an x value to it, and this one will only have a delta y. Yep.
But
This one falls in the negative y. This one goes in the positive x and the negative y. Yep. Absolutely. But the vertical motion is identical. That's what I'm trying to get at. Yes, the green one moves left to right. The red one only falls straight down. But if you think of them as falling objects, they're physically falling at the exact same rate. This one just happens to be moving to the right also. So when we consider horizontally fired projectiles, it's important in the y direction to think of it as a free fall. A free fall. Because a free fall is exactly what you see in red here. You drop an object. That's exactly what Sidney was doing a moment ago. When Thomas rolled the ball, he gave it only horizontal velocity. So when it fell from the table, it was falling and it gained velocity in the y, but so did yours because you dropped it, right? So you both had vi in the y direction as a 0 value for this problem. So let's look at an example of this. Let me jot some of those things down. So for these problems, we could say that vi in the y direction is always going to be 0. And this is for free fall from last chapter, or in this chapter, we're going to say it's horizontally fired. In either of those cases, that is true. Whether it's a free fall or fired horizontally, the velocity in the y to start is 0. But we do have acceleration in the y, we know that, and that's always going to be negative 9.81. And then finally here, if we look at this problem, we recognize what else is happening. Well, along the way, we're going to look for time, we're going to look for VF. Those will be the same in the y direction. In the y direction. The x direction is totally different. And we'll see how that plays a role as well. But this is good to know about the y direction. So notice what I'm doing. I'm going to start using more subscripts when I'm talking about the y direction versus the x direction. I'll have to denote the difference there with subscripts. So let's look at this example. All right. I use Tom Cruise. I like to use Tom Cruise as an example. And I've written these notes like 7 years ago. You know Tom Cruise is, right? You know this? Movie star, actor, whatever. He's like a bit of a lunatic, so I kind of like to, I think he's a funny guy. So. Anyway, he's kind of crazy, yeah. You've seen him lose his mind.
Yeah.
Oh yeah, he does all his own stunts. You'll see that's what part is. He's always doing stunts. So anyway, ready? A bridge, listen guys, a bridge is 300 meters above a river. Tom Cruise gets himself out of a situation, a sticky situation he's gotten himself into. So he jumps off the bridge by physically running. Now, in all movies, what do they do at the edge? They jump, right? They're always, they get to the edge, you just jump. But if you're just like running off a bridge, why does it make sense to jump? If anything, you hit the water harder by jumping. Fun fact. Fun fact. If you're going to ever jump off a bridge, 2 things. 1, throw something right before you. Breaks the water tension. That's what kills most people. Yeah. Fun fact. Take your phone out of your pocket, give up your phone. Actually, if you need to do this for some reason, a bridge is collapsing, or you're, I don't know how this would happen. I know, hypothetically. I'm talking like if you're dropping like 50 feet, 100 feet, where the surface tension can really hurt your body. Surface tension at that much distance is like, it's like cement. I mean, you like break bones. So throw something below you first. It breaks the water tension. Secondly, don't jump off because you give yourself more height to then come down faster again. Okay? So really what you should do, and Tom Cruise, he's an expert, so he knows. So Tom Cruise says, I'm not going to jump off the edge, I'm just going to run off the edge. He runs. Have you seen the Roadrunner or Coyote, Wile E. Coyote? Where he runs off the cliff and he does the thing in the air where he doesn't realize he's off the cliff? Same thing. You run right off. Okay? So, let's draw ourselves a picture. I seem to draw cliffs for everything. I know it's not a cliff, but it looks easy to draw a cliff, so I do that a lot. So here's Tom Cruise, and he runs right off the edge. Yeah, this is water below. That's great. We can do that too. But that's the concept we're looking at. If I call it a cliff, if I call it a bridge, if I say he ends in a death in rocks and he lands in water, it doesn't affect our problem. We don't care how it happens. What we care about are the numbers here, the numbers. Okay? And the numbers matter because then later, as engineers, you use the numbers to make sure people don't do things like this, right? You can't actually. All right, so he jumps off horizontally. He hits the surface of the water after a horizontal displacement of 50 meters. Let's draw his trajectory. What kind of a shape will it be again? Yep, half the parabola in this case, but parabolic. Very good. Okay? It's not perfect, and I don't care if it's perfect. This is what it's going to look like. But what do I draw on my diagram for this 50? Where does that go? Where does the 50 go? And use the key words before the number 50. There are 2 key words there to use. Daniel, what do you think they are? Oh, you both had your hands up. Moreno, go ahead. Yeah. But then, well, no, it was actually both Daniels. Both Daniels had the hands up. Yeah. Prams, go ahead. The person is going southeast, yes, but I'm saying, where does 50 go in the diagram? Is my question. Luz?
It's the horizontal, and it's like 50.
So from where to where, Luz? Use words. From. Make believe it's a cliff if it helps. Don't use it as a bridge. So from where to where? Is it from here to here, from here to here, or from here to here? You have 3 options, right? Yeah. So you would say from the bottom of the cliff to where he lands, right? From the bottom. That's all right. I'm just saying so you can speak the same way you would think. From the bottom of the cliff to where he hits the water. That's 50 meters in this problem. It says horizontal displacement. Horizontal displacement. That's what we know. Now, that's all we know. That's it. And it says if he hits the surface of the water, what is the velocity with which he jumped? So what is the VI in this problem is what we're looking for. You have the answer? You can help?
No, I got confused.
Okay. What is the VI is the question we're asking.
Zero.
No, it's not zero.
That's not about.
In the y direction, listen, remember. In the y direction, VI is 0. But clearly he ran off the bridge, so he had velocity, but what direction did he run? Horizontally. So let's jot this down over here. Let's do this. We are trying to figure this out. What is the velocity? I'm going to break it into x and y, right? It makes it a lot easier. Trust me on this. I know vectors. I recommended tables. I didn't say you have to use the table. It is useful for vectors. This really is useful to use the table. So I want to figure out the velocity in the x. Again, the velocity in the y, though, gentlemen, the velocity in the y to start is what? 0. Is 0. Because Tom Cruise runs horizontally only. He does not run or jump vertically off. He doesn't jump down. The projectile is not fired downward. This is literally a bow and arrow being fired horizontally. Tom Cruise running off the bridge horizontally. They are analogous to each other. So you see how when we do homework problems and I say, if you do enough of these problems, I really can't trick you on the math problems because there's no way to make it any different. A bow and arrow being launched, a shortstop throwing the ball to first, a football player, if it's a quarterback throwing a short line drive pass, maybe like a quick screen pass where there's no loft to it at all, these are all the same scenarios. You need to recognize the analogous nature of problems. So when you're doing this on a test, we're going to do 2 of these, example 1 and 2 for horizontal. They're the same setup. So when you take the test, and I tell you it's now, I don't know, a bullet being fired out of a gun, and it's falling to the ground as a bullet, it's the exact same thing as this. Yes, he's naked. It's up here and there. Okay. Steve was putting your grades into my grade book as he was in the office. We're recording what your grades. They said, yes, Chris's test is missing. I'm like, no, he didn't take it yet. That's fine. All right. So we have these 2. Listen. We have these 2 velocities to start. We have the 2 velocities. Which way does gravity pull us? So what direction is gravity going to be? In the x or y? In the y. It's got to be. Okay. Now, are we taking into account wind at all in these problems? What do we say? Nowhere resistance, right? So, theoretically, listen carefully, theoretically, the wind resistance pushing me back would be a negative acceleration in the x. Theoretically. Listen to that. Make sense of that. If you run through Central Park, you feel the wind pushing against you. You feel air resistance. If you've ever trained in water before, that's even crazier. You feel the viscous resistance of water. In like a 4-foot pool, try to just run in a 4-foot pool, you physically feel resistance. That would be AX, and it would be negative because it's slowing you down. We are not assuming a resistance though. So it makes AX 0. Write this down that this will always be the case here. Put a little asterisk next to AX, put an asterisk, and say for all projectile motion problems, this is true. Now, when you get to AP Physics next year, if you want to take that course, choose to take that course and do well on this one, you can then see what will happen as a result. We're not going to. It makes the problem very different, and the resistance that you feel is a function of your velocity, which makes it a rate of change, and that's where you need some calculus to actually work through the problem. It's not difficult, and a lot of you in this room can definitely do it. But I'm just saying for now, we make this assumption to simplify the problem, to make it a trigonometric problem only. Because you guys know trigonometry, you've learned it. But if you actually have a value here, we have to then use a little bit of calculus to include that value in our calculations. What's that?
So it's for all projectile
Motion.
problems.
Yes. So this is a projectile motion problem. Even if it's fired horizontally, eventually it moves in both the x and the y. Anytime an object moves in both the x and the y, that's what this case is going to be. And this is always true as well. So these acceleration pieces are always, always true for projectile motion. Yeah? Okay? All right, let's continue. So our question, though, says, what is the velocity with which he jumps? So my goal is to figure out this value. Go back to chapter 2, test number 1, chapter 2. When we didn't have acceleration, right? Look, no acceleration. Everybody sees that? When we didn't have acceleration, what was our one formula that we used for velocity? Without acceleration, not VF equals VI plus AT. What was the formula for velocity when there was no acceleration involved? It was the first formula of the year. Yeah, very good. And that is absolutely right. We were able to use this formula earlier in the year because we didn't have acceleration. We assumed that the velocity was, what's the word when there's no acceleration, the velocity is in it, Alex? Constant, very good. Yeah, that's fine. I almost said Andrew first, sorry. So it is constant. The velocity is, I also teach this problem, that's why. No. All right, so the velocity is constant because there's no acceleration. So whatever I start with, take a look up here where I'm pointing, whatever initial velocity I start with in the x, you're also going to land with in the x. Now, the velocity in the vertical is going to change. Why is this velocity going to change in the vertical direction?
Because of gravity.
Because gravity is going to make it go faster in the negative direction. But nothing is causing me to slow down in the horizontal. So although I'm calling this VIX for initial velocity in the x, I can use a bar to indicate that it's a constant. So if you want to call it V bar x, some students have done that in the past. And this is the only, jot this down also. This is the only formula that we're ever going to have to use in the x direction because there's no acceleration. The other three formulas we will use, but in the y direction. Again, jot it down that this formula will always be used in the x direction when doing projectile motion problems. Always, always, always this will be used because there's no acceleration.
Wait, so VIX is equal to?
Correct. It's the same thing. It is not going to change. So our goal is to really figure out what V bar x is or VIX. They're the same thing. Take a look at what I added up here because Alex mentioned it.
So
V bar x or VIX, it's the same thing. So what do we need really?
The time.
Yeah, because look, don't we have x in this problem?
50.
X is 50. It's right here. X is 50. But we don't have the time. Does everybody see this? We don't have the time. Where do you think we might be able to get the time if we don't have it over here?
From the Y.
From the y direction. Let's figure out the time, because remember, time is a scalar. It is independent of direction. Direction doesn't matter. If it takes me 16 seconds to fall, well, you know what? Whether it's the x or the y direction, it's 16 seconds. I'm hitting the water after 16 seconds, no matter what I'm considering, vertically or horizontally. Time is time. So if I can get the time in the y direction, I can use it over here in the x direction. Because my goal, again, is to find velocity, and x is known as 50. Let's jot that down, that x is 50. X equals 50 meters. What else do I know that I still haven't taken into account? What else do I know?
That the bridge is 300 meters above the river.
The bridge itself is 300 meters. This is not drawn to scale. The bridge is 300 meters above the water level. Thus, what do I know physically? Yeah.
He's going negative 300 meters.
In the?
Y.
Very good. So y displacement is negative 300 meters. Think of vectors with the triangle. Remember, this was the vertical component. This is the horizontal component. So we've got 50 as the horizontal, so it's x. And 300 going down, and that's vertically, so that's y. So we have an x displacement, we have a y displacement. You know what, maybe we need to figure out the total triangle, but I don't think we do in this problem. It doesn't say. It doesn't say find the straight line distance, so we don't need the hypotenuse in this problem. Notice that? Remember with vectors, we sometimes found the hypotenuse once we knew stuff. We don't need the hypotenuse yet. We will soon, and we'll see that. And we'll see that in other problems in a minute, in a little while actually. And then again when we find our angles. But for now, I want you to recognize that these are like the components of the right triangles that we've been looking at the whole time. X component of displacement, Y component of displacement. This sign is really important because the object is moving down, the acceleration is down. So if I'm going to call one of these negative, I got to call them both negative. If you want to, you can call everything down positive, but then everything else is negative. You just have to be consistent in your problem. I recommend calling down negative because it's logical and it makes sense, but if you want to just switch your brain for a day and call everything up negative and everything down positive, you can do that. You can absolutely do that. It'll still be the same answers. The question becomes this. If I can't figure out the x direction because I have the following, I know that x is 50, but I don't know time. I need to figure out what time is in the y direction then and plug it in over here. Plug it in over here. So again, my goal is to find the velocity that Tom Cruise jumped off the bridge with, which is v bar x. That's x over t. We know x is 50. We don't know the time. So get the time over here. What equation can I use in the y direction of the big three? Remember the big three from last test, those three equations, not this one. Remember, this is always used in the x, but never used in the y. Because there's acceleration. Some of you on your test, by the way, use this in the y direction. The y direction has acceleration. Can't be doing that, right? So what equation in the y direction can I use based on the given information? I have y, I have a, I have vi. Which of those three equations? Is it vf squared equals vi squared plus 2ay? Is it vf equals vi plus at? Is it y equals vit plus 1/2 at squared? Which of those three formulas fits in the y direction right now? Only one works. Only one works. What do you think? Just look at the three equations, look at the variables you've got. I mean, that's literally all you need to do. Match them up. There's one equation that involves these four variables. What equation, man?
Y equals I don't remember the rest.
VIT plus AT squared. Now remember that I'm only looking at the y direction with this equation, so I'm not confusing this with the x direction. Please, people, do not try to plug in the v and the x here. This is the v from the y. The acceleration here is negative 9.81. It's not zero. That was the x direction. We're done with the x direction right now. We're focused on the y direction. So we can therefore plug in to solve for time. Now, luckily, we don't have to solve a quadratic here. Because what's zero in this case? What's zero in this case? In the y direction, what's zero? VI. So this piece does this. Cross it off. Remember, 0 times anything is 0. Right? We got to remember that. I can't talk about the test right now, so let me stop. But this is 0. This bar right here is 0. Okay, this is stuff that we got to recognize, that 0 times anything is 0. So this equation becomes much easier. Look at what this equation becomes. That's all it becomes. Y equals 1/2 AT squared. Okay? So our goal is to figure out the time. We've got y is negative 300. We've got a is negative 9.81. We can absolutely solve for time. Either plug in numbers and solve for time, or solve for t first algebraically and then plug in numbers. You choose which way you want to do it. I'm going to do it both ways up here. Give me a second. This pencil's dead. I'm going to solve this both ways so we can see the approach. I'll give you maybe a couple minutes yourselves to jot it down first. We have some 12 today. So I want you to take the approach, either plug in at this point for y and a and solve for t. I want you to do it on your calculator, get them out, let's go. Or solve for t algebraically. Solve for t algebraically first in all formulas and then plug in numbers. Either way is fine. I want you to pick which way is better for you. Let's go. If I'm not seeing writing, I'm seeing something that shouldn't be happening, right? I want to see writing. Solve this for time, either with numbers or algebra. Plug in the numbers you're given here to get time. And if I'm timing over here, you get your v in the x direction. So 2 chances or 2 ways to solve this. I'll do both so you can see them both. If I plug in numbers first, I have this. And then I have to double it. I have to divide. I don't know what this number is. And then I have to take the square root of that number. Where did 600 come from? How do you get rid of 1/2? Multiply by 2. Or you can do 1/2 of 9.81 and write 4.905 and then divide by 4.905 and you will get the same number that I have here as a number symbol. What number is that? What do I get when I solve for t squared? Not t, but what do I get here for t squared that I have to replace it with? What do you got, Alex?
61.16.
So what did you get when you took the square root of that, Alex?
7.82.
Now, use the context of the problem in your... Use the context of the problem. Okay? I know, really. Just get out for a second. Okay. Use the context of this problem right here. Do not talk. Use the context. Use the context of this problem. It's plus or minus here. Can I have a negative time in this problem? I can't. I can't have a negative time. So my answer is 7.82 seconds. Luce, what's up? I see your hand float. You sure? So we take that value and plug it in over here. Right? Take this value and plug it in all the way across the problem here for time. That is absolutely acceptable. For those that want to challenge themselves a little bit with their algebra, I'm going to show you on the bottom. Instead, I'm going to show you in black down here on the bottom that if I solve this algebraically, I'll end up with the same solution. So start with this. Multiply by 2 on both sides. Divide by a on both sides. And then take the square root of that answer at the end. Now, I understand that this looks confusing because there's no numbers, but this is the same thing. I multiplied by 2 to get rid of the 1/2. I divided by a to get rid of the a. I then took the square root of both sides to get rid of the square. So this is absolutely acceptable as long as I plug in negative 300 for y right here and negative 9.81, and then you'll get the time. And you'll get the exact same number. But let me show you something really cool. And this is where it becomes like more powerful physics. You can take this expression, take a look, you can take this whole expression and replace time with it. So you don't ever have to actually even figure out what the time is. The problem doesn't care about time. It doesn't say find the time it takes to land anywhere. It says find the velocity. So I don't actually need to do any calculations here. Instead, what I could do, and again, we just did this a moment ago, we can plug in the number, and that's totally fine. And we'll get an answer. Or we can do this. We can put our value of 50, we can take our value of 50, and it just goes over the square root of 2y over a. You could take this entire expression and plug that in for time also. You could plug in a number for time or the equivalent expression for time, but then anyway, you would still have to plug in the negative 300 and the negative 9.81. So in the end, does it matter which way I go? No, it's up to you to choose. If your algebra's getting good and you want to take AP Physics next year and you actually feel confident and you're considering it, you definitely need to do it algebraically and practice it. You have to do that. You'll be all algebra next year. Problems are given without numbers. Literally without numbers. So say the height change is delta y. The acceleration in this problem is a, and you answer in terms of variables. So in terms of variables, this answer is x over square root of 2y over a, and that's the answer. And that's how an AP Physics test would be answered at the end of it. So I want you to visualize already what you'd be doing. You'd be using the algebraic approach. What do we get when we plug in the numbers though? 50 over 7.82. What do we get, McClune? 6.39. And the units are? Velocity?
I mean meters per second.
There it is. Okay, our final answer is boxed in at the bottom here. Around 6.4 meters per second. Meters per second. So I want to make a couple conclusions to conclude today, because we're going to continue in the next class with another one of these problems. We're going to use the actual launcher itself to prove that again, but then we're going to launch things at angles too. Conclusions. First, acceleration for all these problems is always what we see here. 0 in the x, negative 9.81 in the y. That's the first thing. Second, we will always use this formula in the x. Always. Every time. So you don't have to ever even think about it. You always use it. In the y, we have how many choices of formulas in the y direction? How many choices in the y direction? Thank you, Lucy. 3. 3, yes. All the formulas with acceleration are the 3 that we will utilize in the y direction. In this problem, we chose this formula because of the fact that we had all of these variables. Okay, tonight, if you want to, listen carefully, if you want to, you can start this homework. There are a couple of problems that are fired horizontally. It says, any of them firing at an angle? Don't start it. Just wait. Projects. After school, I expect to see people working on projects. I will be in this room with a robotics club teaching. So if you're going to work on projects, it's fine, but you can't do that. I'm going to be teaching stuff on robotics in this classroom.
What is that? Yeah. That's what we're writing in physics. It's physics.
Wait, so what are you going to do during
Velocity.
So he's in soccer, but
And it's
I know, but he's leaving at 2. Half an hour before we get out. What are you going to do during that? Or you
Where's the skateboard? Is that actually kind of
So this example is very similar in nature. It looks like it's different. But again, I want you to see how shooting a bow and arrow, firing a gun, running off a bridge, shooting a package or a cannonball out of a ship. Remember the side of ships? They used to have little cannon entrances, and they would launch cannonballs at the other ships that were there that they were fighting against. Imagine all those scenarios being launched horizontally. It's the same problem over and over. So in this problem, we've got a plane, a specific type of plane that's flying at 500 meters above the ground and needs to drop a package to soldiers on a remote island. So again, think about this already. Here's the plane. The package is here. The package will drop and fall to the island. The same exact motion as Tom Cruise running off the bridge and falling in a parabolic fashion. So the plane moving across the sky is initial horizontal velocity. It's like Tom Cruise running off the bridge. Tom Cruise runs off the bridge and does this. The package from the plane falls and does this. Exact same motion, exact same diagram, but now it's a plane instead of a person.
So the plane's not moving up or down? It's
Correct.
Just
And that's, so we're going to read a little bit further. It says, if the velocity of the plane is 670 kilometers per hour when it drops the package, how long will it take to reach the ground? How far will the package travel horizontally before it lands on the island? So we're talking about a plane at cruising altitude that literally just drops a cargo package.
So the plane's not really...
It's traveling horizontally. Think about any plane. Planes are, upon takeoff, they have initial vertical and horizontal velocity.
But does the velocity of the plane matter?
It does. Why does the velocity of the plane matter? When you're in a car and you take a tennis ball and toss it up in the air, why doesn't it go back and hit you in the face? You ever wondered that before?
Because you're in the car.
Because you're in the car together, yeah, but what about being in the car does it mean?
You're moving with it.
The ball is moving with you. You're in the car's moving at 60 miles an hour, so what's your speed?
So it's not...
What's the ball speed? Everything in that car that's moving together is moving at 60 miles an hour. So when you toss the ball up, you're giving it vertical velocity. It has horizontal velocity of 60 miles an hour. Now, if you toss it out the window, it would shoot back. Why? What are we assuming is not really there? Air resistance. So in this problem, and let me demonstrate it. I mean, it's very easy to see if I do it properly. Watch. Here's the plane. Here's the package. You can literally see it's being dropped and it falls in a parabolic shape. You have to obviously move fast enough, but if you're moving your hand enough, as you let go, where does it move? In a parabolic path.
So the package's initial velocity is the plane's velocity?
Very good. And that's the first piece we want to write down.
That parabolic is it takes the same time as a straight free fall.
Correct, because it's, again,
It's the same.
horizontal. Absolutely. So this is the same problem we saw that ticker tape with the ball yesterday, or when Thomas rolled the ball and Sydney dropped it. The problem was where he dropped it off the edge because it was moving horizontally. So here's our plane moving through the air. Oops. Here's our plane moving through the air. I really can't draw a plane, but it's close. In that direction. Here's a package, and it drops said package, and as a result, that package moves horizontally and vertically. But initially, the plane had velocity only in the x direction of 186 meters per second. Now, if you recall from yesterday, I started that problem by calling it VIX. Remember I called it initial velocity in the x? But then I talked about this symbol over the V, that little line over the V. Why did I use that symbol again? What was that indicating? Good. The velocity in the x is always a constant because we're not accounting for air resistance. So when I look at my x and y direction in a moment, here, what I'll see in the x direction, I can call it initial velocity in the x, but it's the same thing as average velocity or constant velocity in the x, and that's 186. And again, as we wrote yesterday, whenever it's a horizontally fired object, this is always going to be 0. Always going to be 0. Because this plane is not moving vertically. It's only moving across the sky horizontally. So the package starts moving only horizontally. Yes, eventually it falls down, and therefore it gains velocity in the y direction. And we'll talk about those problems later, where we have to find out a final velocity in the y. But in this case, we're talking only about the initial velocity right now, because we know it's fired horizontally, therefore this is 0. What's acceleration in these problems? We said it's always the same for all projectile motion.
AX would be 0, and then AY would be -9.1 meters per second.
Very good. Okay, and those aren't going to change. This is always going to be 0. This is always going to be -9.81 meters per second squared. Now, the rest of the problem we have to figure out. So it says that the plane is flying 500 meters above the ground. Tom Cruise was 300 meters above the water, wasn't he? And where did we use 300 in the Tom Cruise problem?
That's y.
That's the y value. In this case, what is y equal to specifically? Y equals what number?
-500.
-500. Let's not forget the negative because we know here that the object travels down. We don't know how far it moves horizontally. That's what it asks us. How far will the package travel horizontally? And how long will it take to reach ground level? So we're looking for two things here. How far it travels horizontally, x. How long will it take to reach the ground?
Is that like total?
Total t, time. And it doesn't matter which direction. Remember, I can do this, and I can do this. Because it doesn't matter which direction we're looking in, time is the linking variable. Like a link in a chain link, it links the directions together. It's the crossover variable, whatever you want to call it. But recognize that when you get time, it will be the same on both sides. And that's a key to all of these solutions, all of them. It is important to recognize that t is the same in both directions.
Wait, why is the VIY 0?
Again, this plane is traveling horizontally. When it drops the package, what is the velocity? It doesn't throw it down. It drops it, right?
Like
And a drop is always...
It's like the free fall, right?
Anytime an object is physically dropped, the plane does this, and then drops it, its VIY has to be 0. Now, the VIX only comes from the velocity of the plane itself. Only comes from the velocity of the plane itself. Only comes from the velocity of the plane. That's why it has velocity initially in the x direction. And as it falls, it's going to keep velocity in the x. Let me draw a little diagram. This might be useful for us. So let's put the package at a couple locations along the way on the way down. Let's draw a couple dots here. Okay? And at each moment, let's draw vectors to indicate the velocity. Okay? To indicate the velocity. In the x direction, the velocity is never changing. So I'm going to draw the same vector every time. You can do that with me? Okay? The velocity is not changing in the x direction, so the velocity vector is always the same horizontally. It's never changing. There's no air resistance. We said the acceleration is 0 in the x. That's why this is a constant. But in the y direction, what's happening to the velocity? The velocity itself.
It's increasing.
In the
Y direction. Negative.
in the negative direction. So here, it's got maybe a little bit of velocity. More, far more, and then here it's going to even go off the page. Let me just zoom out a little so I can make this emphasis clear. Okay, that's what's happening to the y velocity as it falls. It's becoming more and more and more negative as it falls to the ground. But the key is to recognize that to start, at the plane, when it's physically dropped, this object only has velocity in the x. There's no velocity in the y here. It's being physically dropped. It's got x velocity because the plane is moving. Tom Cruise had x velocity. Why? What was he doing?
Running.
Which way?
Right.
Good. Positive in the right horizontally. Tom Cruise was running horizontally. That's why he had VIX or V bar X. Either one of these terminology. But neither had this.
Why is it constant on that extra? Like,
Because what would cause you to slow down?
distance?
What causes you in general to slow down? What's the word for that? That changes your velocity. Anyway, what's the word when you have a change in velocity? There must be.
Acceleration.
Okay, so the acceleration causes you to slow down, right? What's the acceleration in the x?
Okay.
So therefore, is this ever going to change?
Yeah.
Again, if there were wind, if the air resistance mattered, this might be like -3, -4 meters per second squared. But again, I talked about this yesterday. It takes a lot more math, not just trig, to actually do a problem like that. And unfortunately, until you're in AP Physics and you know calculus with the course, you can't cover those problems. So this is an assumption that makes everything actually much easier for us. So this will always be a constant because there's never air pushing back. But why isn't this a constant? Because gravity is an unbalanced force causing it to accelerate downward.
I was just gonna say, so we can always, when we're setting out the values, we always say that the acceleration of x is 0
Yep.
when it's like horizontal.
Yeah, yesterday, remember I circled this and I said this will never change for any projectile motion ever, ever, ever in this course. Even if it's not horizontal, even if it's fired at an angle in the next section, these will still be the same. Now, these will not be. We'll talk about those in the next section. This will break up into sine and cosine like we did with vectors. But the a values, the accelerations in each direction, will always be a constant. We are looking for time. We are looking for time. And then afterward, we're trying to find how far the island is. So in my diagram, just so we're clear about where things are, this is the y here. And where the object lands eventually, I don't know where it lands, let's say it's here, is x. We know why. Look at the problem. Think about yesterday's problem. What are the similarities? What are the differences? Look at the setup, look at the arrangement, look at your y direction. Tell me what's similar in the y direction. Tell me what's similar in the x. Tell me what's different in the x. What's similar about the y direction? About the y direction. Alex?
They both have the same acceleration.
Good.
And they both have the same VI.
Yeah. In both cases, in yesterday's problem and today, they both had VI y equals 0 and the same acceleration. Now, yesterday's problem said y equals -300, right? Tom Cruise fell from a 300-meter bridge. Today is 500. Any difference?
No, so you just do the same thing. And you're solving for time again.
Yes, and you're solving for time. It's the same approach right now. It's the same approach. So this equation is very important to utilize again. Again, nothing about final velocity yet. We'll get to that part. That's a little tougher. We'll get to that as we go through 4-4. But right now, this problem is the same as yesterday. VI is 0. This thing drops off. Solve for time. And if you think back to yesterday, I solved for time with variables. It became 2y over a under the square root. You could use that same formula and just plug in the new numbers and get the time real quick. You could use the same formula from yesterday that we solved for time. It's the same answer you're going to get. It's going to be 2y divided by a underneath a square root. The same algebraic answer, just a different number. Instead of 300 or -300, we have -500 here. So when we solve this for time, okay, in the y direction, when we solve it for time, we're going to get 10.09 seconds, or 10.1 seconds. Now, this, remember, is one of my answers. It says, how long will it take to reach the ground? So we've got the time. How is the x direction different from yesterday? How is the x direction different from yesterday? Emma?
Yesterday it didn't have the initial velocity of x.
This was unknown yesterday, and what else did we have yesterday? We don't have today. Daniel?
The horizontal displacement.
Yeah, the horizontal.
Good. Good. I was going to have that. Horizontal distance. So we had this yesterday, right? But we didn't have this. Is it any different? Not really. You just solve for a different variable. What's the one equation I told you yesterday that you'll always use in the x direction? Because it doesn't involve acceleration. It's the only one that doesn't have acceleration. What's the equation?
Velocity is a displacement over time.
Yeah. This is the same equation as yesterday. But now, instead of solving for Vx, yesterday we plugged in, we were given x, and we were given time. Well, we found time. Plugged in the time. We had x yesterday, and we found v. Today, though, yes, Alex. Instead, we multiply t up, and we have Vx, and we have t. This is the velocity it started with in the x. Here's the total time we got. Just multiply these two numbers. And again, how do we get that? I'll show. We can multiply both sides by time. And that's what this equation becomes. And then just plug in. We've got 186 as the velocity. We've got 10.1 as the time. It'll give us a length or a distance horizontally of 1877.9 meters. Well, I used 10.09, so that might be off actually if you calculate it. What do you got?
1878%.
Thank you. Okay. And again, you notice on your test, oh, by the way, a lot of you round too soon. I haven't taken off points for that yet, but try to keep numbers until the end. Some people are rounding really soon, like rounding to the nearest whole number when an answer is like, if the time is 0.95 seconds and you're going to use it later, you shouldn't round that to 1. Follow what I mean? Don't round it to 1 too early. Now, it's different if you're, 10.09 and 10.1. Those are 0.01 apart. So significance of numbers should be understood. It doesn't make sense to round if you're rounding dramatically in the beginning, because then you'll use it later.
Wait, so you can't, I don't get why, if it's like acceleration, like why if these Vx equals t.
So remember this formula from the first chapter of the year?
Yeah, but
This involved no acceleration, right?
we have acceleration.
No, we don't. What is the acceleration?
0.
So we don't have acceleration. You want me to prove to you it's the same formula? That's a good question. Watch. You take this formula right here, in blue, right? And if there's no acceleration, this whole thing drops off, doesn't it? So look, x equals vt, x equals vt. So if you want to use this formula in the x and just drop this off every time, you can. See what I'm saying?
Yeah.
When no acceleration is involved, it becomes v times t. It becomes v times t.
So the full answer, meters. The numbers like in the x direction, right?
This is meters because we're in the x, correct?
How does drawing it all affect the x?
Sorry, this was showing in the x only. He was asking about the x direction. He was saying, where does this formula come from? I said it's the first chapter, or you can use this formula in the x and drop off acceleration because it's 0 and you get the same answer. Practice over the weekend. Horizontally fired projectiles. Hey, do more than the 2 I gave you. Maybe look at some of the problem set questions that are horizontally fired also. Right? And then work on your projects, please. Remember, the report is not due on Tuesday for the project because you can't do the report until you do the project. So please do not do the report for Tuesday. I don't expect it to be done. I don't want it to be done.
Mr. Howell?
Yeah.
When's our next test?
Have a good one, guys. Right now it's on the calendar for, forget the date, it's like a Tuesday or Wednesday. It may change, it may stay. I might put it back a day or two depending on how we do it. So it's toward the end of the quarter. It's in the last week of the quarter for sure.
Still counts for this one.
Absolutely, yeah. My concern is right now it's on a Tuesday or a Wednesday, and I can't give it to you on Thursday because it's a C day because we have masses. So if I don't, I have to push it to Friday, which is the last day of the quarter. And if people are absent, that causes problems. Follow what I'm saying? So I'm trying not to change it, but I might have to. What's up?
Jack, for the group for the project, is it okay if he joins my group, or is it just 2?
It's 2 as it was, and I told people that they can't jump into groups last minute because then they're not going to do any work.
Yeah.
So no joining groups at this point. Sorry, let them know, yeah. Nothing personal, just kidding. That's all right. That was the big one. Thank you, everybody. It's all. I do. That'd be great. Good. That's fine. You're absolutely welcome. Yeah.
Only thing I was confused about was I was helping the teacher with the homework, like just getting the concepts down. And for the last problem, when they're adding the vectors, is that just like normal adding the weights, or?
When you're talking about the algebraic approach, where you have to use sine and cosine?
It was like a plus b and b minus a minus b. It was for the last week. I can show it to you sometime.
All right, yeah, come on and show it to me. I'm not sure which question it was. I assigned that homework years ago, so I'm trying to think about it.
I think it was pretty straightforward. I wasn't sure if it was.
I'd have to see it, but yeah, come by and I can go over with you for sure. Thanks, Spencer. Type of problem in this section. So, again, there are 2 types of problems in 4.4. The first type of problem is when the object is fired horizontally. We saw that with the Tom Cruise example. We saw that with the tennis ball moving off the table here that we gave an example, and then with the plane dropping a package. The second type of example is going to be fired, but not horizontally, at an angle. at an angle. And this is where that trig stuff with vector components that we looked at comes into play. So if you recall from vectors, when you want to find the x and y component of your vectors, you use your sine and your cosine. And the y component is always associated to sine, and the x component was always associated to cosine. Okay, that was the assumption we made. Was it really? Did you fix it or did someone else?
My cousin was helping because it was jammed in like literally 60
Is she upset? Okay. Thanks, Steve. So we're going to start by doing a problem with this, but again, I want you to get the idea that if you imagine an object is launched at an angle, it's not only launched up and to the right, it's launched in both directions. In yesterday's class or in the previous classes, we've only been launching things in the x. So we've been saying Vix is some number, and then we kept saying Viy was 0, right? We kept putting Viy to 0 because it's a free fall in the y direction. So we need to picture these two directions independently from one another. Independently. So we're going to see examples now where an object, when it's fired at an angle, needs to be broken into its components first. And then we'll see at the end how we can put those back together. So let's take a look at this second or third example here. So Tom Cruise strikes again in a new action movie. He has to leap from the top of one building to the top of another building. The second building is 4 meters away from and 2.5 meters below the other building, the building he's on. After getting a running start this time, he jumps, but instead of running off the actual edge, he jumps at an angle of 15 degrees with respect to the flat roof, meaning this is your angle, 15 degrees here, not 15 degrees here, while traveling at a velocity of 5 meters per second. And the question is, will he make it to the other rooftop? Is he going to make the jump? So I start again, as always, with diagrams. So if I have somebody running from one rooftop and jumping to another that's below the first rooftop, let's go ahead and draw 2 rooftops. Let's draw the gap here. The gap between the buildings, it says the second building is 4 meters away from the first. So that's this 4 meters right here. And we also know it's 2.5 meters below the other building. That's this gap right here. Now, he's jumping from the taller building to the lower building, or shorter building. So Tom Cruise is going to be jumping from this upper left part here. So let's put a little projectile object right there. And let's show that he's jumping at an angle this time. Remember with vectors, we use the dashed line. That dashed line is so we can draw our angle in there. And the angle in this problem is 15 degrees. Okay, the angle is around 15 degrees here. The velocity that he jumps with, God bless you, is 5 meters per second. Now, what's important to recognize again is that 5 meters per second is not Vx, it's not Vy, it's neither. It's at an angle. So we have to break it into components. Literally the exact same way you did for 4-1 and 4-2. So if I think of this as a triangle, look at my vector here, where the velocity is shown. Think of this as a triangle. The x component is how far he's jumping, or at what velocity he's jumping to the right. This is Vx right here, in green. And Vy is how much or how fast he's jumping vertically. And that's in yellow. But that's what we're doing, just like we did with vectors and vector components. We're going to do that with our vector called velocity. Velocity. So I go to my table method and I approach it the same way as examples 1 and 2. X and Y direction, look at them separately. Exact same approach as example 1 and 2. Again, the only difference is that your velocities are going to be your vector components now. It's no longer going to just be velocity in the x and no velocity in the y that we've had with the last examples when it's fired horizontally. Now, we have a velocity in the x and we have a velocity in the y. And those are my vector pieces. So when I'm looking at the x velocity, and this is never going to change, okay, as long as your angle theta is between the horizontal and the vector, which it is, 15 degrees there, It's never going to change. I'm going to use the velocity itself, which in this case is 5 meters per second, times the cosine of the angle. And in the y direction, I use the velocity itself, again, 5 meters per second times the sine of the angle. Yeah?
Wait, when is the velocity in that x direction 0?
In the x direction?
Yeah.
Only for projectiles launched straight up. And think about last test, right? That was from last test when it was launched up and down, and there was no velocity in the x. So the x velocity in this chapter, because we're launching projectiles either at an angle or we're launching them horizontally, this will always have a value. There's always going to be something for Vx. Guys, focus, don't get distracted. There will always be a velocity in the x direction in this chapter, always. Because we're, again, going to launch at an angle or we're going to launch horizontally, one of those two things. The y velocity is only taken into account if we launch at an angle. If I go back to examples 1 and 2, where the object was launched horizontally, there's no velocity in the y, because again, the y is vertical, and we're launching horizontally in those examples. But when we launch at an angle, we have both velocities. Now, what else do we know in this problem? What else do we know in this problem? And this is a bit tricky, so you have to analyze it a little bit. Don't just tell me everything you see, because some things are not important actually here. Alex, give me something.
Well, the acceleration is gravity for both x and y.
Correct yourself.
Oh, it's 0 for x.
Yeah, always. Remember.
Is that an angle? Wouldn't like.
So remember, which way is gravity pulling you, no matter where you're moving? Down. Always in the y direction, gravity. So in the y direction, it's negative 9.81 meters per second squared, and here it's 0 meters per second squared. What else do we know? All the numbers, thanks. What else do we know? Okay, so this is the part we need to talk about now. So one of two options. What is the question asking us? Because we're going to answer that follow-up in a second. What is it actually asking us? Well, it makes a jump. So we can do one of two things here. You need to really think about this conceptually for a second. We can set the horizontal displacement equal to 4 meters. And then we can find the vertical displacement. And if he's falling more than 2.5 meters, is he going to make the jump? No. But if he's only fallen, say, 1.5 meters, he would make the jump. So if we call this 4 meters, then we have to search to see what our value of y is. That's going to be our unknown. What else could we do instead? And it's either way is acceptable.
You do the y and then find the x.
You could say that y is going to be negative 2.5 meters down. And you know what? After 2.5 meters of falling, is he going to make it 4 meters? If after falling 2.5 meters, his horizontal displacement is only 3 meters, he doesn't make the jump. But if after falling 2.5 meters, x turns out to be, say, 5 meters, then he does make the jump. So we either use x or y in this problem. We're not using both givens. If we say that x is 4, we have to figure out what y is. If we say that y is negative 2.5, we have to figure out what x is. So one of these ways work, both of them work, one is easier than the other. It doesn't matter which one you start because this is the first time we're doing it. You gave us the example and said x is 4. So I'm just going to go with what you said to start. I don't even know if I did it this way in my notes, but it's fine. You can do it either way. So let's say that x is 4 meters in this case. And the question becomes, how far has Tom Cruise fallen after he's traveled 4 meters to the right? If he's fallen more than 2.5 meters, he doesn't make it. If he's fallen less than 2.5 meters, he does make it. Think about position. Think about physically where he is. And I'll use a little dot here so you can see it. So again, if Tom Cruise, after traversing, so here's his jump, after traversing 4 meters, if he ends up falling, say, 5 meters down, he's down here, and he's not going to make the jump. But if after traversing the 4 meter gap, he's only fallen, say, 1 meter, he'd be like right here. And therefore, if he's only fallen 1 meter, he's going to make the jump. So our goal is going to be to figure out what y is and compare our answer to this value right here. Or again, we could do the reverse. We could say that y is 2.5 or negative 2.5 in this case, and figure out what x is to see if he makes the jump itself. Either way works. I want to go through the first process, and then we'll spend a little bit of time analyzing the other method itself. Do we have anything else? Do we have anything else?
We don't have time.
We don't have time, but it's probably going to play a role, right? So let's put down time equals question mark. Okay, it's probably going to play a role in this problem. Time. Remember, time we call our linking variable because if we solve for time in the x, it's the same thing as if we had it in the y direction, and vice versa. Now, based on what we have, I'm going to scroll down so we don't really need the problem anymore. Based on what we have in the x and y direction, would it be logical to start in the x or to start in the y? Just simply analyze it, inspect it, look at the problem, look at the amount of unknowns in both directions, look at the amount of givens in both directions. Which side makes more sense to start in, Gigi? Why x?
Because you have more givens and you know the displacement.
You know the displacement and you're only looking for
Time.
one variable, time. Does that make sense logically? There are two unknowns. Time's always going to be an unknown. So for all these problems, unless you're given the time, you should write time equals question mark. It's always going to be a variable, even if the problem doesn't ask for time. This problem does not ask for time at all. But look at the y direction. To get y, we can't use any of those big three formulas with acceleration if we don't have time. We're not going to be able to get y because we don't have VF. So we automatically can't use VF equals VI plus AT or VF squared equals VI squared plus 2AY. We can't use either of those because we don't have VF. So we have to use y equals VIT plus 1/2 AT squared. But I don't have time. So I can't use this side of the problem, so I'm going to use this side instead.
So once you find the time for the x, then the time is the same for the y.
Correct. We're going to slide it on over. So again, in the y direction, the formula that we're really going to be using is this one. I'm going to start using a lot more subscripts. Okay, so try to keep up with that, what I'm saying here. So y equals, why am I putting VIY? Because the VI is different in both directions. Remember that the x velocity is 5 cos 15, while the y velocity to start is 5 sine 15. Whenever an object is launched at an angle, you're always going to have one and the other component, and that y value goes right here. So VIY in this formula is really 5 sine 15 right here. T is unknown, A is negative 9.81, T is unknown, and Y is unknown. So I cannot use the Y direction because of the fact that two of my variables, being Y and T, are unknown in this problem. Alex?
So you just use the same thing in the x direction?
What's the X equation that we've been using over and over again?
X equals VIX times T plus just the same thing as substitute x.
Yeah, so we could use that same equation, and that works. And I talked about that last class. So you could always use this equation in the X direction.
Isn't there a shorter one?
There is.
Look like x equals v.
That's why it's shorter, right? What's acceleration in the X direction always? Always 0. So this is what my formula really is. And the other way of writing this is to solve for V. If you recall, I also gave you this formula, put it in maybe in the bottom corner over here, from the first chapter of the year that we studied. The formula we used was this.
V equals d with x.
Yeah. And I called it a constant. Remember I used that little bar? Can somebody remind us all why I put the little bar over it? Why is V constant? Why am I putting a bar there? Why is it physically constant in this problem? What do you think? Same too? You guys both just answer questions. Come on, others should know this. Why is velocity constant in the x direction? What causes your velocity not to be constant?
Oh, because acceleration is 0.
Yes. When you have acceleration, it means your velocity is changing. If acceleration is 0, your velocity that you start with in the x is a constant. So whether you call it VIX or V constant x, it's the same variable. It's the same thing. So up at the top up here, if you recall, you could just write it like this. You could write like V bar x is equal to VIX, which is just this number. Your velocity never changes in the x direction for projectile properties, ever. Because there's no,
Acceleration.
because of no what? We make the assumption no
Air resistance.
air resistance. Very good. Air resistance would cause a deceleration. There is none that we're assuming, so we don't have to worry about it. So whether you use what's in blue, right here, or in red, it's the same formula. Again, recognize that these are the same. You got to be able to see that algebraically. This is absolutely identical to this. Just divide both sides by time and you get this formula, right? But what's our goal? What are we trying to determine in the x direction? What variable is the unknown in the x direction?
Time.
It's time that's unknown. So either of these formulas are not solved properly, right? This one is solved for v. This one is solved for x. Neither of which we actually are searching for. We have v. We have x. But we are searching for time. Algebraically, what is time equal to? Algebraically, not with numbers, but algebraically, if I solve for t, what is it going to become? Lucy, I saw you doing it. What's it going to become? If you solve this one by dividing by x, you get 1 over t. Don't forget. If you move this x down, which is what you just did, you end up with a 1 up here still. Why don't you solve this one for t instead? It's a little bit easier to solve this for t. How would you get rid of the v that's multiplying by t? Say again?
Or x over x equals t.
Yeah, there we go. Good. So literally, we're dividing by this guy, moving it over here in the denominator. Or we could physically just switch these two places. Remember, we've talked about this many times now. When you have something that's triangular like this, where something equals a fraction, you can always switch diagonals. So t is equal to x over v, which is the same thing as this. Okay? Make sure you understand that when I write vix or v bar x, they're the exact same thing. They're whatever this is, 5 cosine 15, whatever that number turns out to be. So let's solve for time. Let's figure out what the value turns out to be for time here. I'm going to have the x value, which is 4 meters, over the initial velocity. What does 5 cosine 15 turn out to be? And give me like 2 or 3 decimal spots. Bonaccio, what do you got? What do you got? 1.19? 29.
You get 1.6 seconds because you get 4.9.
You get
4.829.
Check your mode, Bonaccio. Check your mode. It might be in radian mode right now. Classic. It's the same assignment. It's one assignment.
Okay, because there's like half of them happening in the other section. It just seemed like a lot because the other one, this one.
Yeah, I don't know. But it's definitely one assignment. So what's the velocity in the x direction? What was the velocity in the x direction that's going? 4.82. Hey, while we're at it, tell me what this velocity is in the y direction, please. VIY. Oh, that was the sign you used. Okay. And that's 1.29? Before I go further and solve for time, which we're going to do, obviously, we'll get our answer for time over here, and we'll use it in the other direction. Make sense of your velocities. Is this a low-angled launch or a high-angled launch? 15 degrees, is that low or high? Low. What's my mark off, my cutoff point? 45. Below 45 means I'm kicking or launching more in the x direction. Above 45, I'm launching more in the y direction. Look at your velocities. It's a low angle launch, so your Vx is 4.83, while your Vy is 1.29. That is logical. It makes sense. Again, because it's a low angle launch, your velocity is more in the x direction. Low angle, more in the x. High angle, more in the y. Okay, that logical statement has to be there in the back of your mind so you recognize that the answer has some sensible nature to it. The division of that, 4 over 4.83?
83.83 seconds.
Thank you. 0.83 seconds. Now that time, I can take and plug it in over here in yellow. Okay, I know it's 0.83 because if it's 0.83 in the x, it's 0.83 in the y, always. Now, I then simply plug into the formula. And again, notice here, please, I'm not really helping you on the VF problems for this section as much. I'm really focusing on two formulas. This one in the x, right here in red, and this one over here in the y. If we get to a problem with VF, I'll discuss how to get to that piece. And if you have it on a test, it's probably going to be literally just one part for the VF. It's more important that we understand this concept of moving between our sides, x and y, with the main formulas that we've been using. So let's go ahead and plug in. We don't know y, we're looking for it. VIY is 1.29. The time is 0.83 seconds. Plus 1/2 times negative 9.81 times 0.83 seconds squared. I'm going to just drop all my units for now, because I'm running out of space. Right? In my problem, in my answer, I always have units, right? 1.29 meters per second times 0.83 seconds plus 1/2 times negative 9.81 meters per second squared times 0.83 squared. What do I do first? Because I'm telling you now, on the last test, I was very upset. I mentioned this to you already. You need to practice in class. A lot of people will get the problem for the most part right, and then after this, it's just disastrous. You have to square before we multiply everything here. So a lot of people did negative 4.905 times 0.83, and then they squared it. Squaring occurs first, PEMDAS. Exponents before multiplication and division. So please square this, then multiply it by whatever this product is. Then you can take that negative quantity and add it into whatever you get from this first piece right here. So I want values. I want the answer. I want to know what is this product here and what is this value over here, please. Give me first the product of 1.29 and 0.83. What do I get for that piece, Gigi?
1.07.
And then I'm subtracting, because the next part is absolutely going to be negative. What value on the right, Alex?
Negative 3.3, or just 3.3.
No problem. If you round it, is it 3.3 or 3.4? 3.4, thank you. 3.4 or 3.3?
3.4.
Okay. So let's subtract these two values. First of all, it makes sense that my answer is negative, because which way is he falling? Yeah, down. If it's more than 2.5, what does it mean again?
He made the jump.
If he falls more than 2.5 meters, he's not going to reach that cliff. He's going to end up down here at more than 2.5 meters. If it's less than 2.5 meters, he ends up here somewhere. So the idea is that we're trying to figure out what y is and compare it to this vertical gap between buildings. Again, more than 2.5, he's down here. Less than 2.5, he's up here. What do we get as a number between these two? Michaela?
Yeah, negative 2.32.
So does he make it, Michaela?
Yes.
He does make it. He does make it. And let's show where he'd end up. This is his path. Let's use red in our diagram up here. I'll give you a quick projectile path for him. He ends up pretty much right there. Not at 2.5 meters, just above 2.5 meters, where hopefully as he lands, he can step and land and fall onto the actual platform or building. Okay, again, because my number did not exceed 2.5, he's able to make that jump clearly. Yes?
What if your number was 2.5? Like,
Then you would say, like, his foot hits the very edge and hopefully he stays on.
okay.
I'll make it so it's greater than or less than if it's a problem like this, so it's clear that happens or doesn't.
Yeah, how many meters is 1 foot?
1 foot, well, about 3 feet. 3 feet are about a meter. It's like 3.28 feet is 1 meter. So 1 foot is about a third of a meter-ish. Okay? So we're talking about like an 8-foot drop is what this is here, Alex. It's about an 8-foot drop. Okay? Now remember, he's running at 5 meters per second. 5 meters per second is actually pretty fast. 15 feet every second. So we're talking like this is top speed movie star kind of thing where he's maybe, I don't know, able to take some sort of drug enhancement to make him run faster. I don't, you know what I mean? All these movies are crazy stuff.
11 miles an hour.
Is that what it is? 11 miles an hour?
That's pretty fast.
Yeah. Look up the fastest human being.
No, it's like the best thing is like
It's crazy. It's like you're seeing 20 something.
27,
22, 26.
It's like 20 something miles per hour. So it's not impossible by any means, but it's quite fast. Yeah. I mean, if you're running for your life, you'd be running pretty fast.
28.
28 miles per hour?
That's insane.
Which is faster than the speed limit in New York City.
So,
25. Yeah.
pause. Really good example. Now, what I want to do is I want to start something with this projectile launch in a second, but I want to make one more conclusion statement. If we had not assumed x was 4, again, if we had set y equal to negative 2.5, if we had called y negative 2.5, only time would have been unknown over here, right? And then we would have had 2 unknowns over here. So if we called y negative 2.5, we would have solved for time in the y direction, which is fine, it would just been a quadratic, which we'd have to use a quadratic program to solve, or a quadratic formula. Once you get the time in the y, you would have moved it over here, and then you would have solved for the unknown x. And x would be an answer like 4.2. And what does that mean? It means that he makes the jump of 4 meters. So either way you approach this problem, one of your displacements is unknown. It depends on which one it is that you choose. So if you want to tonight, you're not going to have homework for this due tomorrow in this class. If you want to, feel free to revisit this problem. Redo it. There are more room in your notes below. Notability. Assume that y is negative 2.5. Assume that x is unknown. Find time in the y, plug it in, and then find x. That's a very good way to repractice this problem tonight. Okay, it's a good way to practice again. Yeah?
So you're saying x is easier just because of that formula is easier to solve?
Correct, because time is a linear thing to solve for.
Like you don't want to
If you solve for time here, it's a quadratic. It would be 1.29t minus 4.905t squared with a negative 2.5 here. You got to move the 2.5 over and solve the quadratic. So I wouldn't personally do that because it's an easier route, but either works, right? Either method works. Now, what I'd like to do is start this example that we're going to do as a demo. Now, this is a projectile launcher that we can adjust the angle to. Okay, your lab next period, honestly, because I'm not going to have 12 of these gadgets shooting marbles across the entire room right now, and it's actually extremely difficult to make it work and be precise. So your lab next period is going to be a simulation of projectiles launching. It's going to follow the exact same laws of physics that we learned, but because of the nature of this problem, it's going to be a simulation, it's not going to be the thing. So I want to do this as a group also. And in class, so today we're going to just take data. In class, in the next couple of periods, we're still going to finish off the other problems in this section, but also analyze the results of our demonstration. So with that said, I need a couple of things to happen. First, I need someone to move up to this spot, please, and this spot from the back row. Probably people toward the end because you might get hit with a mark. So, yeah, that middle table right there and the end table. This first table, you guys are actually probably good. It's going to clear you for sure. So you can just slide back. But these 4 spots here, you probably want to move over. We're going to use video generator at some point. I'm not right now. We will use it with kinetic energy and potential. We're not going to do it with projectiles. It's also the same thing. It's the same app for freshman year that we're using. Yeah. But it's not one that we're going to use in this section.
Sort of.
Sure, but I'm also going to discuss that's how
Papers out.
So, if afterward you want to stand over
The chair.
Well, you can also do honestly go to Slater's website. There's a solution around that. It's Slater. That's not a complete So you can always check all of your homework.
Never mind. We're good.
I have to walk with you.
That's LAG or
Trash.
Oh my god. Yes, in the last year,
I gotta go over that.
Okay.
Yeah, that was one of the homeworks. Was
Yeah.
that 85? Was that 85?
I think this is it was like throwing baseball this way and this way, so what I do is I contemplate this one.
Alright, next, here's what I need to happen also. So, we need people to be markers of where it lands. So those that are in the back row, you want to help? You're already back there, it'll be easy to do it. So you want to be one of the markers. So what you're going to do is exactly where the marble lands, simply point it out, and then we're going to, yeah, you can turn them on.
We're gonna turn this like just
Turn them on the back, that'd be great. So you're going to mark it off, and then we're going to measure. You want to be a measurer? So you're going to be a marker, a measurer. You want to help with the actual apparatus over here? Awesome. And then you want to do the launcher? Okay. So Steve's going to impression inside of here. There's a photo bead inside of here. So all I want you to do is after so before we run the experiment, we have to and it's going to wait to launch. After it launches, it's going to give you velocity. What you're going to do is you're going to hold down the arm button here. Like you know, the keys, you said return to the key they can do. So hold down arm and press launch. You don't do it already. It's all set up, so don't do it now. We're going to also adjust this angle here in the variables. So all you're going to have to do is read it off. I'm going to have someone else do it. Just read it off each time. So you're going to have a tape measure. Oh, you have it? Awesome. So what you're going to do in 1A, you're going to take this angle now. Hold this up. This has to be lined up with the middle of the launcher. So after you launch it, just make sure this is lined up with the middle of the launcher, and the tape measure should be perfectly straight. So we don't really want to make it slide all the way down here. It's based on where the hand goes. But it launches through the middle. She's going to He's running there right. Don't use metal. We can't slide with this. They're just way too deep. We've done some damage before. Steve, there's only one plastic marble in it?
Is that plastic?
No, I want to use the plastic.
Oh, I wrapped them up in there's a little burrito behind it.
No, only because last year, I think it was announced. Yeah, they were like, What? No, it doesn't go. It goes, I mean, relative. It goes like, the launch velocity is like 6 meters per second. It's not that slow. It says salmon, and this apparently is true. I was saying earlier that I saw something this weekend and it happened to be about salmon jumping upstream. And just for a second, I was flipping through channels. So salmon often jump upstream, actually. The stream comes this way and they actually jump up the waterfalls to reach breeding grounds. So they're starting 2 meters from a waterfall, and the waterfall is 1/2 meter high. At what velocity must the salmon jump if it's jumping at an angle of 32 degrees in order to make it over the waterfall? So it's a bit of a different problem. We haven't done one of these yet. Okay, we have not done one of these problems yet. You're going to see why it becomes a little bit tricky. Okay, but it's not any more difficult than what we've done. It's just algebra. You're going to see the algebra play a role here. Okay, a little bit of algebra, substitution method, that kind of stuff. So let's start with the diagram, right? It helps with the diagram here. So let's start with the waterfall. And let's say, actually, let me draw it the other way so we can draw the salmon jumping to the right. Make it easier. So let's put a little fish down here at the bottom. Okay, there's the fish. And this fish is trying to jump and make it up to the waterfall. And again, your images don't have to be water. Like mine looks like a cliff, right? It looks like a projectile. That's the same exact thing as what's happening here. We know that it's 2 meters from the waterfall. So where does that go in my diagram? Yes, that's this right here. And we know that the waterfall is how tall? 1/2 meter. So this is not drawn to scale, obviously. The angle with which the fish jumps is 32 degrees. Okay, that's the angle right in there. And that's it. That's all we know. That's all we know. Now, first, what's the variable that's always unknown in a lot of these problems that we can use in both the x and the y direction? Time. So time is definitely one of my unknowns. What's my other unknown? What are we trying to find in this problem? What are we searching for? What's the goal to figure out, Daniel?
The minimum velocity.
The minimum velocity. Now, Daniel, is that the initial or the final velocity? Take a minute. No, read through it if you need to. Okay.
Initial,
Why?
because it's starting, so it's like it has to jump with.
Very good. And it says leave the water. With what velocity must the salmon jumping at 32 degrees leave the water? So physically, what velocity are they having when they leave the water? So we are looking for VI in this problem. So we have 2 unknowns here. Those are my 2 unknowns, VI and time. VI and time. The problem is this. Which way is the salmon jumping? Horizontally? Vertically? Neither? Both? Which one?
Both.
Why both? Why'd you say both?
Because it's just like
It's going to go upstream and over.
Yes, it's going upstream and it's going over the waterfall. So it's jumping at an angle, right? It's at an angle. So the problem with this problem is that VI is going to be unknown in both the x and the y direction here. How do I find Vx and how do I find Vy? What's my general thing I do?
Use the angle and velocity times sum of costs.
Very good. So if you recall, from the x and the y direction, let's take a look at what we've got, because this could be a little bit confusing of a problem because we haven't seen one like this yet. We have not seen a problem yet where the initial velocity is unknown. Every problem we've done, of which it's just been 3, right, and then the one we did in class for the demo, we've known the VI value every time. This is one example where VI is not given. It's not given. But we can write this. We can write that V bar x is whatever VI is, we don't know, times the cosine of the angle. And the Vy is going to be whatever VI is times the sine of that angle. Since I know the angle, I can plug those values in if I want to. But I want to recognize again that V bar x and VIY both have a missing piece. VI is missing on both sides.
It's just multiple times cosine.
Yes, sir. The key again is this piece right here. VI is missing in both directions. Now, once I get VI, let's hypothetically say that VI is 5. Okay? Let's just say VI is 5. Well, then V bar x will be 5 cosine 32, and VIY will be 5 sine 32. So these will be different numbers, clearly, right? 5 cos 32 and 5 sine 32 are different. But VI itself as a variable is the same thing. Whatever number goes here, right, is the same number that goes here. Let's make sure we understand that piece. From last class we did this, from the class before we did this. When an object is launched at an angle, whatever initial velocity is, we take that number times cosine theta. We take that number times sine theta to get our components. So that number that's missing, VI, is the same in both directions. It's when we multiply by the trig ratio that makes them different. So we're searching for one variable right now, which is VI. It appears in both sides. It's another type of linking variable. It's kind of like time. How time was in both directions. Well, this VI is going to be associated with both directions as well. Alex, what about you?
Wait, how is it? Aren't they going to be different?
Once you plug them in, they're different, yes. But I'm saying, whatever the initial velocity of the fish was, don't you plug the same number here and here, and then you multiply it by the sine and the cosine?
So the actual, like, what VI is replacing now, that's going to be the same.
Correct.
So let's say it's like 5, it's going to be 5 on both sides, but then when you multiply it by...
Like 5 cos 32 is different. 5 sine 32 is different. You follow what I'm saying? So our goal is to search for the v that was not given in this problem, the initial velocity of the whole fish. Not the x component, not the y component, but the general velocity, which if we draw a vector to show, there's the vi of the fish, right? In blue. So Alex, that's what we're referring to right there in blue. Yes, the fish has an x component and a y component. We can get that by multiplying by the trig ratios. But my goal is just to find vi to start. Okay? To find vi. I also am always looking for t. Always looking for t. It's very useful to have. So let's put for now equals question mark on both sides. What else do we know? Daniel.
We know that the x displacement is 2m, and then the y is 0.5.
And remember, we're not asking the question, will the fish make the jump? That's not the question. Let's make that clear. With the Tom Cruise example, we said he jumped off one building, would he make it to the other? Remember that question was asked? So we had to only assume x is one number, and then we found out what y was, or we assumed the value of y to solve for x, because the question was, will Tom Cruise make the jump? So we had to find out which of these displacements we were solving for, the Tom Cruise example. But this salmon is going to make the jump. We know that. It says, what is the minimum velocity needed to make the jump, to make it over the waterfall, to make this clearance of 0.5 meters. So technically we want the fish to jump greater than or equal to 0.5 meters. Right? If the fish jumps a little bit less than 0.5 meters, it's going to hit the waterfall. No. If it jumps more than 0.5 meters, it makes it above the waterfall. So in reality, we need to find a velocity that makes at least a 0.5 meter jump for this fish, this salmon. Okay? So x and y are both knowns. We don't have to exclude one of them like we did with the Tom Cruise example, because in that problem we were trying to figure out the displacements. Here we're not. Here we're trying to figure out the velocity necessary to make these displacements, to make these jumps. So let's write down what we know on either side of the table here. Now we also know a given that we haven't written down just yet.
Acceleration of the x is 0, and the y is -9.81.
Here's the problem. Here's the problem. How many variables are unknown right now? Yeah.
2.
What two variables are they?
Time and velocity.
Time and VI. Time and VI. On both sides of the equation are unknown, aren't they? So I'm missing time and I'm missing VI over here. I'm missing time and I'm missing VI over here. So I can't find time on one side and plug it in like we've done in the past because we have enough information in the past. So here we're going to have to use substitution method. And let's go through how that works. Let's write down what we know. What's the formula we're definitely going to use in the x direction? We've used every single problem in all of chapter 4. We always use this in the x direction. What's the one formula?
Velocities and displacement over time.
Yeah. This was our standard formula in the x direction. It's not going to change. On your test on Friday, this will be the absolute formula you will use in the x direction. You have to. Because remember, acceleration is 0. Whenever acceleration is 0, this is the formula we use. Now, the problem is we don't know the information. V bar x, well, that's VI times the cosine of 32. X is 2, but then time is unknown. So look at this formula. I've got two variables unknown, time and VI. Time and VI. So I cannot solve for time. I cannot solve for VI explicitly with a number. I can't plug in numbers because I don't have the information. So let's go to the y direction and see if maybe the y direction helps us. And this is how I would approach this problem if I were a student. I would stop at this point and say, oh, look, two variables. So I need two equations. So let me move to the y direction to get a second equation. That's what I would trigger in my head. As soon as I see two unknown variables, I can't go any further with this equation. There's no use in me trying to solve for VI. Yeah, I can move the cos 32 down. Or maybe solve for t by switching these whole things, t with this entire thing. We don't know which one we're going to solve for yet. So let's move to the y direction. In the y direction, what's the variable that is not included right now? What's the one variable in the y direction that we don't have? And it eliminates two of my formulas right away. It eliminates two of my formulas right away because we don't have it in the y direction. What variable don't we have in the y direction? I mean physically, we literally don't even see it. It's not listed here at all, anywhere. Lucy? VF. VF is not listed, right? Is this problem about final velocity? No. Is this problem about the velocity of the fish on the way up? No. What is it about? It's about an initial velocity. The problem is about an initial velocity, not the velocity on the way up, or when the fish lands, or impact velocity, when it's about to splatter or land there, right? It's not about that. It's about initial velocity. So right away, rule out the VF formulas, which leaves you with one formula only. As soon as you rule out the two VF formulas, you got one left. Okay, by now we should know what that is. Get Alex.
X equals VI times t plus 1/2 AT squared.
Very good. And I'm going to use subscripts like I did yesterday or Friday, your class, Thursday, Friday. Okay, I'm going to use subscripts. I'm going to put y instead of x, Alex, because it's the y, but right? It's the y variable we're looking at here, vertical displacement. So remember, please, these are subscripts. This is VIY. This is AY. These are not variables. If you need to write that, write yourself a note, because I can tell you now, just from looking at handwritings and homeworks, if it were me, and I look back at my notes, and I saw some of the handwritings that I've seen in the room, I might think this y here is a variable. If I'm looking at my notes later on, I might think that this y is a variable. It's not. These are subscripts over here. This is a variable for y. This is 0.5 right here for y. That's the height that the salmon needs to achieve when it jumps over the waterfall. These are subscripts indicating that I'm in the vertical direction. Okay, but I'm honest. I'm not trying to be mean. I'm being completely honest with you. Just based on looking at some handwritings in the room, I think that some of you might make a mistake when you're studying for your test and think that this is a variable for y. They are not. They're subscripts, so make sure they're nice and small or denoted a little bit lower.
When you have a problem that's wanting to find minimum and maximum velocity, you know it's going to be the y because the x velocity is always constant.
Yeah, if you're searching for velocity, it's always the y you're searching for. Even yesterday or the other day when we did it with the projectile, we tried to find the time after, or the velocity after 0.15 seconds. Remember, we said Vx was constant, so we only found Vy, and then we put them back together with the Pythagorean theorem. So whenever you're finding a velocity, inherently, you're finding velocity in the y direction, really. Now, this is one of those cases where we don't know what Vi is, so we don't know the V bar x either. So this Vi turns out to be in both spots, but yes, inherently we're looking for the y direction when we find final velocity for a problem. Let's plug everything we know into the y direction here. Alex, what's up, guy?
I was going to say, wouldn't it make more sense to just substitute it and then put everything in, or?
It could if we knew what we were doing, but right now, I don't know, should I solve for time, should I solve for VI, and then plug it in? So I'm going to plug numbers in first to show, so we can visualize and see it. I would know because I've done enough of these, but if you haven't done these problems yet, they're kind of new, this type. So I want you to see it first. So let's plug in a 0.5 for the y value, that's the height. VIY is VI times sine 32. And that whole thing is times time, minus 4.905 t squared. So recognize what I'm plugging in, people. That's VIY. That's VI in the x, right? Take a look at all I'm doing is plugging in my given up here. VI sine 32 goes in right there for VIY. Times T goes times T. Half of 9.81, we should know this number by now. 4.905. It's going to come up over and over. So if you don't want to show the substitution every time, I don't want to waste the time to find the time. Okay? We're looking for T, which is unknown here and here. We're looking for velocity, which is unknown here. We're looking for T, which is unknown here. We're looking for velocity, which is unknown here. But what I notice now is I have two equations, don't I? I've got an equation here, and I've got an equation here. So believe it or not, at this point, and I'm going to use the word simply, I know it's not simple, but it's simply algebra. It's all it is. It's substitution method. What did substitution method tell you last year, 2 years ago in Algebra 1 when you learned about it? Substitution method. What is the whole premise behind substitution method?
Solve for one variable in terms of the other.
Solve for one variable. Very good, Bridge. Good word. In terms of the other. In terms of the other. Now, what are we trying to figure out in this problem? Are we trying to find out the velocity or the time? What was the actual goal? I know they're both unknown, but what's the real goal of the problem? What are we searching for?
Velocity.
Velocity. So even though time is in between here, I kind of really don't care about time. I don't care about what time turns out to be in this problem. So, write yourself a note. Since we are looking for VI, put a little asterisk or something, right? Since we are looking for VI, we should solve for time. Since we are looking for VI, we should solve for time. Since that will eliminate time as a variable. Since we're looking for VI, solve for the other variable, time, because it will inherently eliminate it from the problem. Since we're looking for VI, solve for time, since it will eliminate it from the problem. Now, X or Y direction. Can I solve for time in both directions right now? Is that possible? Alex, you're saying no.
It's possible, but it's just like not able to.
Yeah, but I mean, with all that, with this variable here, it makes this pretty much impossible because there's time in two spots, right? So which side do we solve for time?
On the X, and then you just switch
The whole thing, please. The whole thing switch. So go ahead and flip-flop VI cos 32 and T in the X direction. In the X direction, again, let's go ahead and solve by flipping those two. So T equals 2 over VI cosine 32 degrees. Now take this expression for time and plug it in here and here. This is where it gets to be a little bit of algebra that I was saying here, substitution method. Yes, there's sines and cosines, but that just involves typing it in a calculator. Don't let that overwhelm you at all. This is algebra. It's all it is. It's algebra. Okay, we're plugging in for time in both spots. It's going to look a little bit difficult to solve, and we'll go through this together, but I want you to recognize that it's really not difficult if you step through the process one step sequentially at a time. So I'm going to plug in for time with that expression in the y direction. I'm going to kind of move this up a little bit so we can see a little bit better. So I'm going to plug in and write down what it becomes. We have 0.5 equals VI times sine 32. That remains the same. It doesn't change. Times this whole expression, which goes in for time, minus 4.905. Again, times the whole expression. And that expression at the end is going to be squared. So where I'm putting those big parentheses sets, you got to write this entire expression. So I'm literally taking the expression for time over here, plugging it in here, and here. That's what you're seeing in red. Now, again, it looks overwhelming, and I know right now some people might be a little bit like, oh my gosh, God bless you, God bless you. How am I going to solve for this, right? Like, what's going to happen? But there is some nice cancellation that's occurring. Anyone see a little cancellation that I can do right away? What can I cancel right away? Alex?
If you divide that, just you can cancel out the in red. Or no?
Cancel out, say again, Alex?
Like if you divided the, I don't know.
It's more obvious, so you're probably not seeing it. Gigi?
You can still VI.
Where, Gigi?
The first VI was sin 32 and then VI was cos 32.
Yeah, not this one, obviously,
Not
right?
that
So recognize, take a look over here, people, if you didn't see it. This is really important that you see this. This is really over 1, isn't it? Any number by itself is over 1. Cancel this VI with this VI. They can cancel each other for sure. They absolutely can. Now, we're not concerned about this one. We're going to worry about this one in a moment. But it's this one we want to cancel.
Could you cancel the 32?
So sine 32 is a number. Cos 32 is a number. So we can't cancel those. Now, later this year, although you may have learned it already, you'll learn about the fact that tangent can be defined as sine over cosine, actually. You probably have seen it in your geometry course last year real quick, but that might not have been something you memorized. Now, it doesn't matter. You don't have to replace, because this is sine 32 over cos 32, you could replace it with tangent 32. But because you have a calculator on the test, you can just type in sine 32, type in cosine 32, and do your math with those numbers. You don't need to use the tangent feature. But let's cancel the VI's, because that's really important. Without those canceling, this becomes a really complicated problem to solve, right? Where we're looking for VI, it's missing here, and VI squared over here. It would be like a quadratic in the denominator, it would be really messy. But because they cancel, it simplifies the problem a little bit. And you'll have a problem where they would cancel, okay? Let's continue down. 0.5 equals. Can somebody give me a number? We have. And do it carefully, please. If you're going to use your calculator, when you do sine 32, you got to close your parentheses before you multiply by 2. And then divide by cosine 32. Give me a number for this expression right here. I want 2 times sine 32 divided by cosine 32 to give me a number for this first term over here.
Did you need degree or
Degree. Always degree. Until you get to your math course where you learn about radians, everything's in degrees this year. Until you get to that point in your math class.
1.25.
1.25?
Yeah.
That sounds reasonable. Now watch what I'm going to do next. Watch what I'm going to do next. So again, all we did was take this times this divided by this, and that's what it gives me. Okay, remember to do 2 first. I'll put a little arrow so we know where that came from, okay? Now, on the right side, I need to square everything inside that parentheses. Well, 2 squared is an easy number to figure out, right? 2 squared is simply 4. That's the easy part. That's just a 4. But then I got to square that denominator. Now, cosine 32, type it in your calculator, see what you get.
0.84?
And then square that number. And give me like 3 decimal spots, please.
0.719.
So take a look at what I'm doing. I'm simply processing through the algebra. I'm doing it in the right order, though. I made sure here to simplify these 3 terms into this. And then over here, 2 squared is 4. VI squared is VI squared. Cosine 32, get that number, square it, and you should get 0.719. It will work, I promise, and I told you guys this will get easier as well. You'll recognize, oh, we're using the same formulas again. Oh, it's the same kind of problem again, right? Now, it becomes a little bit tricky because, again, it's just a little bit of arithmetic and algebra involved here. So if it were me, and I were doing this, and it were like a test or an assessment, what I would do next is this. I would take negative 4.905, I would multiply it by 4, I would then divide that by 0.719 to get a number for these 3 together, leaving this alone in the denominator. Okay, it is the best way to continue from this point. So this will be 0.5 equals 1.25. Now it's going to be minus for sure, and it's going to be over VI squared. But again, I want to get a number from the product of these and the quotient of 0.1719. So get a number there, and let's bring that number right there into the numerator. So again, 4.905 times 4 divided by 0.719 gives me
Negative 27.29.
27.29.
Yeah.
And I carried my negative down here. And I carried my negative down there. I'm trying to go super slow today. I would not go this slow for me on a test. I'm trying to go slow to show you guys the work. So again, I would do the multiplication of these two, divided by this guy to give me that number. Leave the VI squared in the denominator. Last, we'll give you a question. Ask questions if you're confused about the algebra, and I'll pause and go back. I'll point it out if it helps.
Okay, so then you subtract the 1.25.
I would subtract this guy over here next, making this a negative 0.75 equals negative this number over that, and then do the switch again, the triangular switch. Any questions though before I do that? Before I go to the next line that Alex just asked? Any questions about the algebra from here down pretty much? So algebra and arithmetic, right? I keep saying algebra, both of those things together. I know it looks like a lot, yeah?
Is it, so it's the 4.95
Times this, divided by this, gives us this right here. Yep, very good. And think about the way that works. When it's all numbers, right? This comes out to be like, this is really 5 times 4 is around 20. And 20 divided by a decimal should get bigger. So my answer of 27.29 is reasonable.
How does that get above VI squared?
So the VI squared is in the denominator already. So you can't move it because it's a variable down there, right?
That wasn't canceled out.
This one canceled out here and here. But remember, we substituted this whole expression in here and in over here. So the VI that was on the right side never dropped off. It carried down. It canceled over here, which is why we had these three numbers that gave us... Because we're squaring it. Remember this term? The T whole thing is squared, so I have to apply the square to all three things. Hey, this is a rule that a lot of people make mistakes on. When you have something like this, the squared gets distributed to all of these things because they're all factors. These are all factors inside of the parentheses. So the square applies to all three of these. Let me put a little circle in yellow to show this part, by the way, in case this was confusing. That's the number that becomes 1.25. Okay, sine 32 times 2 over cos 32, that becomes 1.25. At this point, let's move the 1.25 over. Subtract it from both sides. What should I do to get VI by itself? What did we do earlier? Just switch it. Literally flip-flop. A double negative? Oh, look at that. That's not a coincidence. Remember, we're going to have to take a square root, aren't we? So this number has to be positive, and it's a double negative, thus positive. So go ahead and find the quotient of 27.29 over 0.75. Then take the square root of that.
6.03.
Somebody verify that, please. Make sure that Alex's work is correct.
Yeah, that's right.
6.03. Now, plus or minus? Plus or minus?
It's plus because it's velocity, it's going up and to the right.
Yeah. And if we look back at the problem, let's look at the wording of the problem. At what minimum velocity must the salmon jump to make it over the waterfall? So we're trying to find the lowest velocity. The lowest velocity. So what does that mean? What does it mean about this answer? It's a lower bound. So what other numbers would work that the salmon would successfully make it? Give me another example of an answer where the salmon would make the jump. Or do you go even further, which is fine. As long as the salmon doesn't make the jump. The goal is to make the jump. So what other kind of numbers?
So any number equal to or greater than 6.03.
Very good. Any value greater than or equal to 6.03 works. We were finding the minimum velocity necessary to make the jump. So 7 works, 8 works, 9 works, but again, our answer is technically, for writing it technically here, our answer should say that VI is greater than or equal to 6.03 meters per second. That's our final answer, really. And again, the goal was to find the minimum velocity necessary to make the jump. There's a lot of work in this problem. It's not easy by any means. Okay, you have to practice for sure. You really have to practice.
How many did those get the test?
So you can expect on your test to definitely have a vector problem where you have to make a vector table and break it into components, and one of those you'll have on the test. And you can probably expect to have 2 4-4 problems that have maybe parts A, B, and C where you have to find a couple things. And I'll try to be nice and step you through the process as you go through by asking A, then B, then C in that order. But you can definitely expect one vector algebra problem where you use the table method, cosine and sine to break up the vectors from 4, 1, 4, 2. And then probably about 2 of these types of problems. Maybe I'll give you 3 and say choose 2 of 3. Yeah, but they'll take you maybe, if you're actually practiced, if you're practiced 7 to 10 minutes maybe to do one of these problems, they're lengthy. If you're not practiced and you come into this test cold, I mean, this might take you 25 minutes for one problem, easily. But what I mean by practice is like if you were playing sports and you were practicing, you would get better at that skill. The exact same thing is in this sense here, right? If you practice something, it's easier on you. It will take you much less time to do it.
Wait, so would that be the answer we give you?
I mean, it says at what minimum velocity, so you could say that VI must be greater than equal to this, or you could say the minimum velocity needed is 6.03 meters per second.
I have a question about what the multiple choice will be based off on the test. Will it just be based off the notes?
It's always theory, yeah. Anything that we talk about. So like we've talked in this class in the last section, in the last meeting, when we talked about the max height problem. We talked about how the velocity in the y direction is 0 at max height. Yet the velocity in the x is always a constant, right? We've done things like we've launched the day when Sydney and Thomas threw the tennis ball. Remember the tennis ball at the edge of the table? So an object fired horizontally or an object in free fall, well, it takes the same time to land. Like those kind of conceptual problems will show up in your multiple choice and your middle of the test. But for the math part, you could probably expect one example where it's fired horizontally, because we've done a whole section of that in the first 2 examples, and then one example where it's fired at an angle. Okay, but they're fair game. Any of these examples can play a role. Alex?
Wait, so for the one with the line on the table, if they both hit the ground at the same time,
They did, yeah. Whether it's launched horizontally or free fall, they hit free fall. They hit the ground at the same time.
but they don't follow the same path. So
Correct. One falls straight down, the other one falls parabolically. So it's delta x that differs. They have the same delta y in the same time, but delta x is what's different in that problem. Yeah. I want to start the last one just to begin it. Okay, I want to begin this last problem here. So number 5 says a daredevil is shot out of a cannon at 45 degrees to the horizontal. 45 degrees is a good angle we're going to use. We've already talked about it. You guys have already seen it in your lab when you tried to find maximum range. So consider that concept. 45 degrees to the horizontal with an initial velocity of 25 meters per second. A net is positioned at a height of 11 meters above the ground. At what location to the right of the cannon should the net be placed to catch the daredevil, the person, the acrobat, right? It's like if you go to like a circus, you would see this. Now, we have to draw a figure of this again. So here's our object or our person getting launched from a cannon at 45 degrees with initial velocity 25 meters per second. The net is 11 meters above the ground. So let's just put a net somewhere. Make it look like a basketball net. I know it's got like a bottom to it. Okay, that's the net. Now, I know that the net is 11 meters above the ground level. Okay, we know that much. But what's the question we're trying to figure out? Daniel?
Looking for the horizontal displacement.
Well done. We are trying to figure out where should it be placed horizontally. At what location to the right of the canyon? So we're trying to find out what x is in this problem. I got a question for you. We've done this problem already. We've done it already. When does the object reach a height of 11 meters? How many times is that going to happen? How many times will this daredevil reach the height of 11 meters? I should see everybody saying 2, right? 2. Why 2 times? I see a couple of you saying it. Why 2 times? That's it. On the way up and on the way down. Now, let's be logical. I'm an acrobat. Do I want to be launched up into a net, or do I want to be landing in the net? Landing in the net makes more sense, doesn't it? It really does. It's logical. So this problem is going to be portrayed like this. That's the problem we're looking at. And yes, it reaches a height of 11 meters twice. Once here and once here. The 2 red dots. Take a look at the 2 red dots. That's when the acrobat reaches a height of 11 meters at both of those dots. Which one do we care about? We clearly care about the later of the 2, the second time that the acrobat reaches this height. When do we get 2 times as answers? Help me out here. When we solve a what? Do we get 2 answers for time? Quadratic. So what does that mean directionally we're going to look at? The x or the y to start probably? Which one involves a quadratic? Does the x ever have a quadratic? Have we ever had a quadratic in the x? No. We haven't. So it's probably going to be the y direction, right?
T squared.
Yeah, probably something with a t squared. Which formula had a t squared in it? Oh, that's right. And notice, are we concerned with velocity at the end of the problem? No. We're not trying to find VF anywhere. So there's a good chance that we're not going to use the VF formulas. So we're going to go ahead and use the formula that we used in the last one. Let's go ahead and write these down. We don't know the x displacement. We don't know the time. That right away tells me I can't use the x direction, but I can write down at least that I know this. This is going to be 25 cos 45. I know that already. Remember, whatever your VI is times the cosine of the angle always gives you the V in the x direction. In the y direction, we know the height it's going to reach. It needs to reach 11 meters. We don't know how much time it'll take. We know the velocity in the y direction. Well, it's the same as the x except with the sign. And then we also know acceleration in both directions. Yeah, Gigi.
When will the y be 0? Is it when there's only no angle and it's only one horizontal and higher?
You mean the velocity of the y?
Yeah, sorry, the y.
Yes. When it's that's a great question. When it's horizontally fired, DIY always goes to 0. That's the change in the problem. But besides that, these problems are the same that we've been doing in this chapter. They're all the same, except this drops to 0, and Gigi, this just becomes 25 then.
Okay.
Because if it's only fired horizontally, all 25 is in the VX. Okay?
Wait, so if it's horizontally fired, the VIY is 0?
Correct. Okay. The Y displacement is 0 if it starts and ends on the ground. That's another possible type of problem to look at. Not this one right now, but that's just another thing to write down if you want it. That the Y displacement, instead of being 11 meters, would be 0 if it started on the ground and ended on the ground. Or started on a building and ended on a building with the exact same height as the building next to it. Now, we're probably going to run out of time in a second or two. Here's what I'd like. You have the formula in the y direction to use. Here it is. And before we solve it, let's write down the formula in the x as well. What's our goal in this problem again to find? What are we really searching for in this problem, Alex?
X.
Correct. So let's take this formula and solve it for x. Okay, that's the formula that we're going to really be concerned with. So take a look. We have v bar x. That's 25 cos 45 right here. Right? And that goes in for v bar x. So what do we really just need? We need time. We need the time it takes to reach 11 meters as a height. And then we can get the x displacement. So let's go to the y direction and plug everything in. This is 11. 25 times the sine of 45. I don't have a number for that. I didn't write it down. Can somebody tell me what that is?
17.6.
God bless you. So look how much easier this problem is than the last one. Why is this problem so much easier than the last problem? Yes. When we have two unknowns like initial velocity and time in the last problem, it makes it tricky. But we've got VI. VI was 25 at an angle of 45, so this is VIY. 25 sine 45 is 17.6. That goes right here. This is, let me jot it down so we all know later where that number came from. This value here is 17.6. Hey, by the way, this is also 17.6. That's not a coincidence that these are both 17.6. It's because of that 45-degree angle. So you can solve for time with the quadratic formula or by quadratically on your calculator. Take the answer for time, the larger of the two answers, because we're trying to find the second time. Plug that in here to get x. Remember, your report is due tomorrow for your project. Make sure you get that in. And you can pretty much start your homework at this point. That'll be due in a couple of days. Your lab is also due tomorrow, correct? Okay, so make sure that the project can be printed or submitted to Drive as a PDF. Printed or Drive as a PDF. You want to find one project per group if you did it with a partner. You don't need two different ones. And if you work with a partner, one report is fine. If you work on your own, obviously you have your own report. This is one time that I do own honesty because it's just time. It's easier to grade less than this one.
And in the
The y is -1. Very good. Very good. The y is -1. How come y is -1? Chris?
Because like the overall displacement, like it's when it hits the ground, but it started at 1 meter up, so it's kind of like a fall.
So it goes down. It ends up below where it started. Remember, the punter is kicking this ball from 1 meter above the ground.
Oh, so it lands.
It lands on the ground, so that's a meter below where it landed. So y is like our delta. Remember, y is our change in height or displacement vertically.
I don't know, like, impact velocity is just fine.
Well, let's figure out what that means. We're also given theta first, right, of 20 degrees. And the impact velocity or impact speed is what we're trying to figure out, and the time it takes to land is what we're trying to figure out. So impact speed and time, we're looking for both those things. So I could put time equals question mark. Chris?
Yeah. That's VF.
Yeah, but remember, when we're looking for impact speed when it hits the ground, we're looking for the overall value of VF, technically an absolute value, because we're looking for speed.
Right.
So we really need to recognize here that the x velocity is a blank. What's the word again? The x velocity is always a constant. So the x velocity is going to be, as Daniel said, 12, which is the initial velocity times the cosine of the angle. The y velocity to start, remember the y velocity is only to start because it's going to change. How come the y velocity changes? How come the y velocity changes but the x doesn't change? What's happening?
Because it's just accelerating positive
You tell me, what's the acceleration sign? It tells you.
and negative.
Yeah, it's negatively accelerating downward in the y direction. There's gravity pulling it down. So although it's launched up initially like this, gravity's pulling it back to the ground. But the whole time through, it's moving to the right. It's always moving in the x direction. It's never slowing down in the x direction because there's no acceleration in the x direction. There's no acceleration. So at the end of this problem, remind yourself, please, with a diagram if you have to right now. Your goal is to find VF. And VF is really whatever V bar x is. Now, what do you think is going to happen if it's hitting the ground? Which way should I draw VY? Vy should be down if it's going to hit the ground on the way down, right? It's landing, it's impacting the ground. So Vy will be drawn this way at the end. And our goal is going to be to figure out this red vector represented here. And we'll call that Vf. I'll try to move this Vx. Hold on, if I can move it, of course I can. Just for now, I'll cross it off so you can see it better, okay? So that's going to be our goal for this problem. Sure, we're looking for the time, but I'm really just giving you the steps along the way. I asked you to find the time first, thinking, well, you know what, we'll find the time of flight here, and that might help us to figure out the final velocity. I'm not sure.
So this would just be like the VF and VF.
So remember that when it hits the ground, I want you to just think about it first, right? An object is punted, it follows this trajectory, and watch the object. As it hits the ground, look at the angle. It's angled into the ground and to the right. That's into the ground is VFY, the velocity angling down. To the right is Vx, but really it's at an angle. We want to know the overall velocity, not each little piece. So what we'll do is be able to use this number here because it's never changing in the x direction. We can find our final velocity here, pull it into this direction, and then use Pythagorean theorem to find the overall velocity. So we're going to put these pieces back together, kind of like how we deconstructed vectors and then rebuilt them to find the resultant r. We're doing the same thing. We're using our x piece and our y piece to build the vector back in.
Would, if you're asking for impact velocity, would you be finding over at y?
Yeah, and if I said velocity technically, you should also find the angle, because velocity indicates a magnitude and a direction. So that's why I said speed here. When I say speed, you're going to take the positive of whatever this is, because it's definitely positive, it's a length. And you're not going to account for the angle.
Okay.
Okay?
Wait, so as it's like in the y direction, it's just going down more time.
Well, in the beginning it's going up, but it's being pulled down the whole time. Like right now it's slowing down the y, slowing down the y, it's 0 in the y. Speeding up negatively in the y, speeding up negatively in the
Yeah, but
y.
you can't end speed.
I'm saying speeding up and negatively in that direction. That's all I'm saying. Yes, the speed itself though is a positive value. Absolutely. Okay? So in this problem, if we look at this a little bit further, like we just did with the diagram, what we'll recognize is, first, to get VF, magnitude, speed at the end, we need the overall VF, which means we need Vx. Well, we've got that, so that's good. So we need VF in the y direction, really, is what we need. But unfortunately, to find VF in the y direction, well, actually, we could use another formula. What formulas could we use to find T and VF in the y direction? There's multiple options here to which way you want to approach. I'm asking you for time and for VF, both. So you can go in that order, or if you want to, you could switch up the order, actually, and use another formula. Chris, what do you suggest we do?
The VF squared. VF squared equals VI squared plus 2AX.
And because we're in the y direction.
Sorry, Y.
Yeah. And I'm using all my subscripts again. So I can use this formula right now because I know the displacement, y. I know the acceleration, gravity. I know the initial velocity in the y direction, 12 sine 20. So I can plug all these in and find the final velocity in the y direction before finding the time. You can do that. If it's a test and in part A I ask you to find the time, you're going to need to find the time itself, and then you can probably use that in part B. Or you could find the VF here to help you find the time in part A. Follow what I'm saying? You can do neither order. Let me show the example of why this works. So let's solve it this way. Let's go ahead and plug in. So the initial velocity is 12 sine 20, right? What does that give me as a decimal with maybe 2 spots? What's 12 times the sine of 20 become?
It's 4.1046.
I'm going to leave them all there just for the sake of rounding. Plus 2 times negative 9.81 times negative 1. So this will give me the final velocity of the object in the y direction. And this is the second part of the problem. So we can start this way. Or we could have done time. It doesn't matter which one we do first in this case. Okay, it doesn't matter. But if we do this one first, it might help us for the second part for time. And it'll make time a little bit easier. We won't need a quadratic if we do it this way, actually. What does VF become when I take the square root of that right-hand side? Right, do the 4.104 squared, add on that positive value at the end, take the square root. What do you get for VFY? It's just calculator work at this point, right? Yeah, I see something typing away. Right, literally, type it in the way you see it here. This is definitely positive, right? We see this double negative, that's positive. It's got to be adding on. So 19.62 plus around whatever this 16 is, square rooted.
36.5.
The square root of that, right, is what you should have. Second square root, second answer.
Yeah, 36.46.
6.03.
6.03 becomes the velocity when you square root it. Is that? Is it 04 if around?
Well, it depends on how many decimal points you put in.
I know, that's the thing, guys. Again, so one of these things you'll notice is this. If you square this, type this all in one line, then square root the whole thing, all on your calculator without rounding, your answer may
You'll
be
probably get like an answer.
But it's around 6, right? Around 6?
Yeah.
Now, once we have that value, we've got the velocity of the y. Are we going to choose negative or positive for this answer? In the y direction when it's hitting the ground.
Negative.
Why negative? I heard negative. Can somebody give me a justification?
Because it goes down compared to where it started.
Yeah, upon launch, the launch is upward, right? Upward and to the right. Still upward to the right, still upward to the right. Now, just to the right. Then, downward to the right, downward to the right, downward to the right until it hits the ground. So it's hitting the ground on the way down, so we need to choose the negative sign here. And that's indicated already in my diagram here. You all see that? This arrow is drawn down for that reason. Because the impact velocity is going to be to the right and down. So this is going to be 6.04 meters per second. What's v bar x when I just do my quick math on my calculator here? What is 12 times the cosine of 20 give me? 11.28. Thank you. So again, make sure we jot these numbers down in our table maybe to make clear where they're coming from. Oops, what was that? 4.104, right? See where I'm jotting down my velocity? So we know that I'm actually evaluating this number, getting a velocity, and then using that velocity later on. So how do we get VF, or what do we do to get VF here? Quick work through Pythagorean theorem. What do you got?
Oh, I didn't do it, sorry.
Tell me the steps, though. I'm doing what here?
11.276 squared.
Plus.
6.03 squared equals VF squared.
Sum these two squares
It's like
together.
12,
Take the square root.
12.8.
12.8. And remember that we're taking the positive value of this no matter what, because we're being asked to find the impact speed. So we don't need to worry about the direction it's angled at right now. We're not looking for theta. If we were finding the resultant vector with magnitude and direction, we would need theta here. Okay, remembering theta is right here. This is theta right here always. God bless you. It's always between the vector and the x-axis that it extends from the initial point of the vector. Remember, start with the initial point of the vector, extend the x-axis, and then find the angle between that and the vector. That's theta right there. But we're not doing that in this problem because we're not asked for the direction of impact. We're just asked for the speed upon impact. So 12.8 meters per second. Now, we completely we worked around the time. We didn't find time in the first part there at all. We could have found time in the first part and then used time to figure out VF if we use VF equals VI plus AT. So we could have done that, right? Again, we could have found time first and used a different formula to find VF. But now that we've got VF in the y direction, we could probably find the time using another formula also. So normally I would tell you to use this formula. I would say, oh, you know what? You know y. You know VIY. You don't know time. So let's go ahead and use this formula and find time. And that's what I would normally instruct you to do. Again, this is negative 1. This is 4.104. Negative 9.81. This is a quadratic. You could solve a quadratic. Agreed? Now, because of the nature of this problem, think about the ball starting here, ending here. It's only going to reach a height of negative 1 once, not twice. Think about it logically. It starts here, it does this, and it hits a height of negative 1 when it hits the ground. It doesn't hit the ground twice like the problem we were firing it up. You see the difference of what I'm saying right now. If you're firing an object to a higher height, it's going to reach that height on the way up and on the way down. But if you're firing an object to a lower height, it only reaches that lower height once. So the other time you're going to get is going to be what kind of a number that we're going to reject automatically. What kind of time? A negative time.
Oh, you're.
So when you solve this quadratic, if you do this problem, you will definitely get a negative time, which is as if this punter went back in time to reach a negative 1 height. Think about the parabola. When you start the parabola here, and you end up all the way over here, imagine having gone backward in this direction. That's the time kind of you'll get there. So you're only going to take the positive time if you use this formula. And I would have probably started my problem this way, because if I asked to find the time first, I would have probably found time first. But Chris suggested using this formula to find the VF first, which is fine. But again, if we had used this formula, we found time, we could then have used this formula. I should put my Y's. We could have used this formula to find VF after we found time. Again, if we found time first, we plug in time, we know VI, we know acceleration, we can get VF, right? So Chris shows the way to get VF in the blue font. You see the blue writing here. We could have taken this red approach as well. But now that we know VF, it doesn't make sense to use a complicated formula such as this to find time. Because you would have to solve a quadratic, right? We just said this is a quadratic to solve. Now that we know VF, we could probably just use this formula to find time. We have VFY, there it is. 6.04, and this in this case is negative 6.04. Remember, we chose the negative sign here because it's going down. VIY is given us 4.104. Acceleration is there. We can absolutely find the time of impact using this simple formula at the bottom. So again, if you were taking the root where you're starting with the blue formula here, VF squared equals VI squared plus 2AY, I would absolutely jump from this answer right down to this formula here. I would disregard this formula altogether because you don't need to use this formula to find time if you have VF already, and that's the way we approach this problem. Okay, so let's plug in what we know. We know that the final velocity in the y direction is negative 6.04. We know the initial velocity was 4.104. And this is plus negative 9.81 times the time. The key is to remember that this is negative. If you don't make this negative, the problem will not be right. Okay, it's reaching negative 6.04 when it's on the way down in the y direction. That's the key to make sure that this is negative that you choose. So this is plus or minus, I get that. And it doesn't matter which one you choose over here. Whether you choose negative or positive here doesn't matter because we're squaring it, right? But it does matter if we choose the negative here. The velocity is on the way down impacting. What do we end up getting for time when we solve that? Right? Subtract the 4.104, gives you around negative 10. Take negative 10 divided by negative 9.81. It should be a little more than 1, your answer for time. What do we get, Gigi? 1.03 sounds about right. So we look at a problem like this and we recognize, hey, we can find VF first and then find time. Let's do the same problem right now. And I know it's annoying, you're like, why do we do the same one? Because I want to prove to you that no matter what way you choose on the test, it does work. So there's not always one right answer. You'll notice that on your last test, that when I went over that, if you came to office hours or if you've looked at the solution online for the math part of the last test, there were a couple of problems where it had multiple ways to solve, and I wrote or for that reason. So this is one of those cases. So this was one way to solve it, by finding VF first in the y direction, that was here. I'll put a little dashed box around it. By finding VF first in the y direction, then using that VF to find the total VF, and also using that VFY to find the time. The other way to do this problem is to find the time first. If we did that, let's just prove that it works here. So to find the time first, again, we'd use this formula. We know everything in this formula except for time. We know that the object is starting at the punter's foot and ending a meter lower. So y is negative 1 right away. That's given in my actual givens right here in the table. I then take this 4.104, look where I'm pointing. Take this 4.104 and place it right here for VIY. And what's half of negative 9.81? We should know this number by now.
Negative 4.905.
Yeah, it's the same number every time, right? So take a look. We end up getting a quadratic if we do it this way to solve for time, like I mentioned we would, of which one of those answers will be negative, and you'll reject that answer. So why don't you do it on your calculator for practice real quick. Let's go ahead and solve this quadratic. I'll put it in standard form, but it doesn't have to be if you're using the graphing tool. Okay, remember if you're graphing, it does not have to be in standard form. If you're typing it into a program that you've written with A, B, and C, you need to know which are in the right order. So it's in order now, A, B, C. But again, if you're graphing, just get it equal to 0 and put it in Y1. It doesn't matter the order in which you type it in your graphing calculator. Once you've graphed it in Y1, go ahead and find that x-intercept to answer what the time is. And I want to hear both times. I know one is negative, but I just want to hear what it is. If you have an error, it means you used a minus sign instead of a negative sign. Or a negative sign instead of a minus sign. The negative sign is at the bottom of the keypad next to the decimal. That's where the error would probably, if not, it might be another issue and I can combine it.
Yeah,
Hey, if you're, you know why?
I get 1.03.
If you're getting an error, you know what else might be? You might have your stacked plots on it. Remember from your statistics stuff you've done in math? Didn't you guys do line of best fit recently? So if you press y equals, then in the top left it says plot 1 and it's highlighted, go up there and unhighlight.
No, it's not.
Yeah,
It works online. The program we did together.
I haven't heard of it.
Then I don't know. So
Oh my
try
god, I
to
got it.
get the
Did it have 6 calculators?
No, it's not negative 1, it's positive.
So this one?
You gotta add the 1.
Oh my god.
So you got, sorry, you mean Alex, or Michaela, what do you got?
I got negative 0.197
And?
and 1.0.
We're just talking about.
This is kind of a terrible pun, Sal.
A hang time of 1 second.
20 degrees.
Is that a boost line? Is that like a 40-yard?
It's like a
Is that 40-yard line?
swift punt.
No, they're called push punts.
Yeah, much like you
So
can.
you get a low liner so that it actually lands somewhere low and you're going to go wrong like 40-yard down.
I thought that's usually though. I thought they kick it even higher. Like, I thought they just kick it higher instead of more.
I guess they would go higher.
Like, so they go like. I thought you know. So usually you do a 45 degree angle, right? But then I feel like if you're close. All right, but like okay, let's say 60, right? Whatever, give an angle like at
Either way,
regular
20
pun.
degrees.
But I
20
feel
degrees
like
was
if
arbitrary.
it was close, if you were closer to the other end zone, I feel like you go a higher angle.
Yeah, to be honest, Chris, they didn't give an angle in this problem. It was kicked, and I think the goal was to figure out theta, which we haven't done yet. So I just threw an angle in there for 20 degrees.
No, not realistic.
Not bad, not bad. So 70 degrees. We do
That'll
all
screw me up.
Yeah, do the whole round once again. That's not. So it really doesn't change much, though, right? When you think about it, you would change these two pieces here, and then accordingly change the rest. Now, what we'll notice from this problem again is that our time that we get as an answer is the same, whether we do it this way up here, or taking the VF and the Y, using it here, and then plugging it in. It's the same process we would utilize to figure out the time. All right, let's do another one. Or let's, you know what, let's make a list of types of problems. I think that was asked before. So we have problem 1. Listen. Problem type number 1. Launch and ending at the same height. Again, problem type number 1. Launched from and landing at the same height. This is the easy way to categorize these right away. Problem type number 2. Launched lower, ends higher, or launched higher, ends lower. It's pretty much the same problem. They're symmetrical, those ones. That's problem type number 2. In those cases, your y value, right? In this case, y is equal to 0. In this case, y is equal to a positive number. And in this case, y is equal to a negative number. That's the thing that differs in those 3 problems. The next type, the max height problem, starts here, ends at max height. In this problem, we know that VFY is equal to 0 always. This is the max height problem. I'm just writing down the keys that we have to recognize for some of these. Let's see. So that's the max height. I mean, we could also do the reverse of the max height, which I haven't really asked you much of, but on the way down. Let's say from max height, we'll call this problem. And in this case, instead of thank you. Instead of VF being 0, what would I write in this case? Very good. In this case, if it's starting at max height, that's the initial part of the problem, and that would be VI equals 0. Okay, from max height. The impact velocity problem. Let's say that the object starts here and could end at any location along the way. This is the impact speed problem. And in this case, we have to recognize that we need to find VFY and then use V squared equals Vx squared plus Vy squared. That's the one that we just did a minute ago. The impact speed problem.
So impact speed is basically like the absolute value of the impact velocity, because it's like there's no.
Yeah, because remember the angle theta is what tells you whether it's going down or right or stuff. So we're not worried about that when it comes to speed. Remember, this can be at any point along the way. That's why I put 3 dots here. Okay, I put several dots showing that you can find the speed here, 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 any point along the way using this formula always. Okay, putting back your 2 pieces of velocity back together. Number 5 is the horizontally fired problem. And in this case, VI is equal to V bar X. And VIY is equal to 0 in this problem. Remember, this problem is the horizontally fired. This is the one that we started the chapter with. Since we've done that one in the first beginning, examples 1 and 2, right, is classical problem number 5 here. Say again? Yeah, it's something where you have to land lower than you started. You have to land lower than you started. So let me draw the path of the trajectory. Yeah, like that. Good point. Okay, so these are really your 5 main problems. I don't think we've done it. Unless honestly, tell me if it's another one that I'm forgetting, because I want to include it. Is there another type of problem that you've had for homework that differs from these? I mean, you have to find different things. Sometimes you find the x displacement, sometimes you find the time. But have there been any other types of problems than these when you look at the arrangement?
Which one's the one where the swimmer jumps and you have to find her speed?
Impact speed when hitting the water?
The impact speed one?
When hitting the water?
Yeah.
Did the swimmer jump out?
Yeah,
horizontally?
Jumped out. And it's like, yeah, they gave us an X and a Y value.
But did the diver jump up and out or dive out?
Wait, let me check.
A diver runs horizontally.
Okay.
So that's the 5th
That's this one here with combining this formula here.
Oh, okay.
So remember, the impact speed problem, it can be started by launching upward or you can launch it horizontally. But when you want to find the impact speed when it hits this location at the end, this red dot, you utilize this formula again. Vx would be whatever the Vi was to start. This would be 0 to start. To start, this would be 0. You'd have to find Vfy again. So you could combine those 2 problems while you're doing it. Which would be really good. Emily?
For the impact speed problem,
That's fine, Emily.
what is the equation? So,
This right here?
yeah.
This is just Pythagorean theorem. So what I'm saying is,
Oh,
find the
okay.
x velocity. Find the x velocity.
Emily, I was so
Make sense though?
Yeah.
It was one of the
This
next.
is your x velocity or your y velocity.
You said it's an A squared plus B squared plus C.
That was the limit what it is. No, I mean, it's a triangle.
I really hope we don't.